You might think our solar system is a well-mapped, familiar place. After all, we've known about the planets for centuries, sent spacecraft to most of them, and charted their paths with incredible precision. But the reality is far stranger and more uncertain than that comfortable picture suggests. Time and again, scientists have discovered that what seemed settled and complete was actually just the beginning of deeper mysteries. The outer reaches of our cosmic neighborhood remain largely unexplored, filled with objects that move so slowly and shine so dimly that we're only now beginning to notice them. Even today, in an age of powerful telescopes and sophisticated computer models, we may be missing something enormous, something that could change our understanding of the very system we call home. We'll be exploring this possibility in more depth in this video and learn more. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. The outer edges of our solar system hold secrets that stretch the limits of what we think we know. Neptune sits about 30 times farther from the Sun than Earth does, but even Neptune isn't the boundary of our cosmic neighborhood. Beyond it lies a wilderness of ice and rock, where objects drift in orbits so vast that a single year can last 10,000 of ours. Astronomers have started noticing something curious out there in that darkness. Small, icy worlds, each just a few hundred kilometers across, seem to follow eerily similar paths around the Sun. These aren't random wanderings either. They cluster together, like leaves floating along the same invisible current in a pond. At first, this looked like coincidence. Space is enormous, and patterns can appear where none actually exist. But the more distant objects astronomers found, the stronger this alignment became. These small worlds move as if something massive is gently tugging on them, something hidden in the outer darkness. This invisible influence might be a planet, possibly many times larger than Earth, orbiting so far away that no telescope has ever glimpsed it directly. Scientists call it Planet 9, though the name feels almost playful for something so mysterious and remote. The idea isn't entirely new in astronomy. We've discovered worlds through their gravitational fingerprints before. Neptune itself was found this way, when mathematicians noticed that Uranus wasn't following the orbit it should. They calculated where an unseen planet would need to be, pointed telescopes in that direction, and there Neptune was, exactly where the equations predicted. But distance changes everything in ways that challenge our imagination. Light from the Sun grows weaker as it travels, and the relationship isn't simple. A planet 10 times farther away doesn't just receive 10 times less sunlight, it receives 100 times less. At the distances proposed for Planet 9, our Sun would appear as nothing more than a bright star in an alien sky. Such a world would exist in cold that defies everyday understanding. Not winter cold, not even the brutal cold of Antarctica, but temperatures so extreme that gases we consider permanent parts of our atmosphere would freeze solid. The surface would know darkness, broken only by starlight, and the faint glow of distant worlds. Yet even in that profound isolation, gravity would continue its patient work. The planet would trace its enormous orbit, taking perhaps 10,000 years to complete a single journey around the Sun. Think about that span of time. Entire human civilizations could rise and fall between one season and the next on such a world. The evidence for this hidden planet comes from mathematics, rather than direct observation. Computer simulations suggest that the clustered orbits of those small outer objects make perfect sense if a large planet is shepherding them gravitationally. Remove that planet from the equations, and the tidy alignment falls apart, scattered into randomness that doesn't match what we actually see. This detective work represents astronomy at its most patient and methodical.
Scientists study the movements of worlds they can barely see to infer the presence of one they cannot see at all.
It's a reminder that the universe often reveals itself indirectly, through subtle influences rather than obvious displays. The search for Planet 9 continues with increasingly sophisticated tools and techniques. Modern telescopes can detect incredibly faint objects, but space is vast and searching it requires both precision and luck. The planet, if it exists, might be anywhere along an orbit larger than any we've mapped in detail. Some researchers remain skeptical, suggesting that other explanations might account for the orbital clustering. Perhaps the pattern results from observational bias, or maybe multiple smaller objects create the same gravitational effects as one large planet. Science advances through such healthy disagreement, with each theory tested against new observations. The possibility raises profound questions about planetary formation. How would such a massive world end up in the outer darkness? Did it form there originally, condensing from the same disk of material that created the other planets? Or did it migrate outward over millions of years, pushed by gravitational interactions with Jupiter and Saturn? Some models suggest Planet 9 might even be a captured object, a wandering world that formed around another star entirely before being gravitationally snared by our Sun. The galaxy contains billions of such rogue planets, ejected from their birth systems and drifting alone through interstellar space. The temperatures on Planet 9 would create an alien landscape unlike anything in our earthly experience. Surface features would be sculpted by processes we can barely imagine, where familiar substances behave in completely foreign ways. Methane and nitrogen, gases in our atmosphere, would form solid mountains and plains. If the planet has moons, they would orbit in a realm where seasons last millennia, and the sun provides less warmth than a candle flame. Any geological activity would be driven by internal heat rather than solar energy, creating a world that generates its own faint glow against the cosmic night. The orbital mechanics of such a distant world challenge our understanding of planetary systems. Most planets we know about, whether in our solar system or orbiting other stars, follow relatively circular paths. Planet 9 would travel an elongated ellipse, sometimes coming closer to the Sun than Neptune, other times retreating to distances where interstellar space begins to dominate over solar influence. This extreme orbit would create a world of incredible contrasts, though even its closest approach to the Sun would still leave it unimaginably cold and dark by Earth standards. The differences between its nearest and farthest points would span distances greater than the entire orbit of Jupiter. Modern sky surveys continue mapping the outer solar system with unprecedented thoroughness. Each new discovery adds another piece to the puzzle, either supporting or challenging the Planet 9 hypothesis. The work requires extraordinary patience, as objects at these distances move so slowly that tracking their orbits can take years of careful observation. Whether Planet 9 exists or not, the search for it has already expanded our knowledge of the solar system's architecture. We've discovered dozens of new objects in the outer regions, each one helping to map the complex gravitational landscape that shaped our cosmic neighborhood over billions of years. The mystery reminds us that even our own solar system holds surprises, that the familiar map of planets and moons we learnt in school represents just the beginning of a much larger and stranger story. In the patient darkness beyond Neptune, worlds may wait that dwarf our understanding of what's possible in the realm of our own Sun. Throughout the centuries, humanity's perception of our cosmic neighborhood has been one of constant surprise. The boundaries we draw around our solar system keep shifting, like a map being redrawn with each new discovery. Ancient civilizations looked up at the night sky and saw what they thought was a complete picture. Saturn marked the edge of everything, the final outpost in a universe that seemed knowable, manageable. The invention of telescopes changed everything, though gradually. Uranus emerged from the darkness first, then Neptune. Each discovery pushed the frontier a little further out. These worlds had been there all along, of course orbiting silently in the cold depths, but human eyes simply couldn't reach them. There's something humbling about that, the idea that entire planets can exist just beyond our perception, waiting patiently for us to develop the tools to see them. Neptune's discovery stands out as particularly elegant. Mathematicians noticed that Uranus wasn't behaving quite right, its orbit wobbling slightly, as if something unseen was tugging at it. They calculated where this invisible influence should be, pointed their telescopes in that direction, and found Neptune almost exactly where their equations predicted. It was mathematics made visible, a triumph of human reasoning over cosmic mystery. This success bred confidence, perhaps too much confidence, Scientists began to believe that anything significant lurking in the solar system would eventually reveal itself through gravitational effects or reflected sunlight. The assumption seemed reasonable at the time. Large objects should leave traces, clues that careful observers could follow. The early 20th century brought another surge of optimism. Astronomers launched a systematic search for what they called Planet X, another world beyond Neptune. The motivation came partly from tiny irregularities in planetary motions, partly from the sense that the solar system felt incomplete, like a story missing its final chapter. Clyde Tombaugh eventually found Pluto in 1930, after months of comparing photographic plates, looking for a speck of light that moved against the background stars. The discovery sparked celebration. Headlines announced the ninth planet, and Pluto took its place in textbooks and children's imaginations. For decades, it seemed like the solar system had finally been mapped completely, but Pluto turned out to be smaller than expected, much smaller. As observations improved, estimates of its mass kept shrinking. It became clear that this tiny world couldn't possibly account for the orbital disturbances that had motivated the search in the first place. Those irregularities were eventually traced to measurement errors rather than gravitational influences from unknown planets. The story took another turn in the early 2000s. Astronomers began discovering other objects in the outer reaches of the solar system, bodies similar in size to Pluto, scattered throughout what we now call the Kuiper Belt. Suddenly, Pluto wasn't unique anymore. It was one member of a whole population of icy worlds, remarkable but not exceptional. This forced a reckoning with the very definition of what makes a planet. The debate wasn't really about Pluto itself, but about how we categorize the objects we find in space. Should size matter? Orbital characteristics, the ability to clear neighboring debris. The discussion revealed how much our classifications depend on human preferences rather than natural boundaries. Pluto didn't disappear when it was reclassified as a dwarf planet. It's still there, still fascinating, still a world with its own moons and seasons and weather. The demotion stung for many people who had grown up memorizing 9 planets, but it reflected a deeper truth about scientific knowledge. Our understanding evolves, sometimes in ways that challenge comfortable assumptions. The solar system once again became a place of shifting boundaries, uncertain edges. Just when we thought we had drawn the final map, new questions emerged from the darkness, and now, perhaps, those boundaries are shifting again. The hypothesis of a 9th planet, sometimes called Planet 9, emerged not from a single dramatic observation, but from patterns hidden in data. Researchers noticed that certain objects in the outer solar system seemed to cluster together in their orbits, as if something massive was shepherding them. Computer simulations suggested that this clustering could be explained by a large planet, perhaps 5 to 10 times the mass of Earth, orbiting hundreds of times farther from the Sun than we do. If such a world exists, it would be what astronomers call a super-Earth, a type of planet that appears common around other stars but strangely absent in our solar system, at least in the regions we've explored so far. The irony is striking. We've found thousands of planets around distant suns, many of them larger than Earth, but smaller than Neptune. Yet our own cosmic backyard might be missing this entire category of world. Planet 9, if it's really out there, would be hiding in almost perfect darkness. At such distances from the Sun, it would receive virtually no light to reflect. Its orbital period would be measured not in years but in centuries or millennia. It would creep across the sky so slowly that its motion might be undetectable for decades. Searching for such an object pushes the limits of current technology. Even the most powerful telescopes can only survey small patches of sky at once, and the search area is enormous. The planet would appear as nothing more than a faint dot, barely distinguishable from countless background stars and distant galaxies. Astronomers describe it as looking for a dim ember in a field of glitter, knowing only that the ember should be somewhere beyond the horizon. This is patient science, the kind that unfolds over generations. Teams of researchers scan the sky methodically, building up databases of observations, watching for anything that moves against the stellar background. Each survey eliminates some possibilities while opening up new regions to explore. The work requires a particular kind of dedication, the willingness to search for something that might not even exist. There's something almost meditative about this process. In an age of instant communication and rapid technological change, the hunt for Planet 9 unfolds at a cosmic pace. Years pass between significant developments. Entire careers are built around refining the search, improving techniques, ruling out false alarms. The difficulty of the search itself tells us something profound about the universe. Even in our own solar system, mysteries can hide in plain sight. Space is vast beyond human comprehension, and darkness is an excellent disguise. A world larger than Earth could orbit our sun undetected, not because it's impossible to find, but because the search space is so enormous and the signal so faint. This realization carries a certain comfort. Despite all our technological achievements, despite satellites and space probes and detailed maps of planetary surfaces, the cosmos still holds secrets close to home. There are still questions waiting quietly in the dark, still discoveries that haven't been made yet. For much of recent history, the solar system felt like known territory. Textbooks presented it as a tidy arrangement. The sun surrounded by planets, following predictable paths. Mercury, Venus, Earth, and Mars formed the inner group, small and rocky. Beyond them stretched the realm of gas giants, Jupiter with its swirling storms, Saturn with its magnificent rings, then Uranus and Neptune, cold and distant, but clearly part of the family. This picture felt complete, reassuring in its orderliness. Astronomers could calculate planetary positions years in advance. Spacecraft could be guided across billions of kilometers with extraordinary precision. The solar system seemed not just known but domesticated, a cosmic neighborhood where every address had been mapped and catalogued. Yet this sense of completeness depended on looking at the brightest, closest objects, the ones that reflected enough sunlight to be easily visible. Mercury flashes briefly during twilight. Venus shines brilliantly as the morning or evening star. Mars glows with its distinctive reddish hue. Jupiter and Saturn dominate the night sky when they rise above the horizon. The outer reaches remained largely invisible, too dark and distant for easy observation. What we couldn't see, we assumed wasn't there, or at least wasn't important. This assumption shaped scientific thinking for generations. The solar system had edges, and beyond those edges lay empty space, scattered with comets and debris. Recent decades have shattered this comfortable picture. The Kuiper Belt revealed itself as a populous region filled with icy bodies left over from the solar system's formation. Beyond that lies the scattered disk, where objects follow highly elliptical orbits that carry them far from the sun before swinging back toward the inner regions. Some of these distant objects show orbital characteristics that seem almost too coordinated to be coincidental. Their paths align in ways that suggest a common influence, something massive enough to shape their motion over millions of years. Computer models consistently point toward the same explanation: a large planet in a distant, elongated orbit. The evidence remains circumstantial, patterns in data rather than direct observation. But the patterns are compelling enough to drive continued searching. New telescopes come online regularly, each one offering slightly better sensitivity or wider coverage than its predecessors. The search techniques grow more sophisticated as well, using artificial intelligence to scan through vast databases of observations, looking for objects that move against the background stars. Meanwhile, the theoretical work continues. Researchers refine their models of how Planet 9 might have formed, how it could have migrated to its current orbit, what effects it should have on other objects in the solar system. Each new calculation helps narrow the search, focusing attention on the most promising regions of sky. The hunt for Planet 9 has become a test case for modern astronomy, demonstrating both the power and limitations of current techniques. We can detect planets around stars hundreds of light years away, but a world in our own solar system might still elude us simply because it's so far out in the cold and dark. This paradox reflects something fundamental about exploration and discovery. The most obvious questions aren't always the easiest to answer. Sometimes the most important secrets hide in the places we haven't thought to look, or in regions where looking is simply difficult. Whether Planet 9 exists or not, the search for it has already transformed our understanding of the solar system. The outer regions are no longer seen as empty space, but as complex dynamic environments, where gravity and time sculpt the orbits of countless objects. The boundaries we once drew so confidently have dissolved into gradual transitions, regions where the sun's influence fades slowly rather than ending abruptly. Perhaps that's the most important lesson. The universe doesn't respect human categories or comfort levels. It's stranger and more complex than our models suggest, full of surprises waiting to emerge from data we haven't collected yet, or patterns we haven't recognized in observations we've already made. The search continues, patient and methodical, driven by the possibility that our solar system still has secrets to reveal. In the vast darkness beyond Neptune, something might be waiting to rewrite the textbooks once again. For generations, humans gazed up at the night sky and believed they knew the limits of their cosmic neighborhood. Pluto marked the edge, a lonely sentinel in the darkness. Beyond it, astronomers thought, stretched empty space. But the universe has a way of humbling our assumptions, especially when we peer into its most distant corners. The late 20th century brought us sharper eyes, more sensitive instruments that could catch whispers of light from the solar system's furthest reaches. Slowly, like pieces of a vast puzzle revealing themselves, astronomers began finding other icy worlds beyond Neptune. At first, just a handful. Then, dozens. Then hundreds. These discoveries painted a completely different picture of our solar system's outer regions. What we once thought was empty space turned out to be teeming with ancient remnants, frozen chunks of rock and ice, left over from the solar system's chaotic birth. We call this region the Kuiper Belt, and it stretches like a vast donut around the sun's outer edge. Pluto wasn't alone anymore. It was just one member of an entire family of distant, cold worlds. Some of these newly discovered objects were shockingly large. Eris, found in 2005, turned out to be nearly identical in size to Pluto, but actually more massive. Other dwarf planets followed, Haumea, Makemake, each one challenging our neat, orderly view of the solar system. This flood of discoveries forced scientists to make a difficult choice. In 2006, they redefined what it means to be a planet, creating a new category for these smaller worlds. Pluto found itself reclassified as a dwarf planet, joining Eris and the others. Many people felt like something precious had been taken away, but really, we weren't losing anything. We were gaining a far richer, more complex understanding of our cosmic home. The solar system wasn't shrinking, it was expanding in ways we'd never imagined. What seemed like a tidy arrangement of 8 planets around a star was actually a layered, intricate structure extending far beyond the familiar orbits we learned about in school. It makes you wonder what else might be hiding out there, waiting for our instruments to become sensitive enough to find it. One of the most fascinating things about these distant objects is their incredible patience. A world orbiting far beyond Neptune might take hundreds, even thousands of years to complete just one trip around the sun. From our perspective, watching these objects for a few decades is like glimpsing a single frame from an incredibly long movie. We're seeing just a tiny fragment of their eternal dance. This creates a peculiar challenge for astronomers. How do you figure out the shape of an orbit when you can only observe a small portion of it? How do you predict where something is going when it moves so slowly that entire human generations pass between meaningful changes in position? It requires remarkable patience, the kind of science that unfolds across lifetimes. But as more observations accumulated, patterns began to emerge from the darkness. Some of the most distant objects weren't behaving randomly. Their orbits shared strange similarities, the points where they came closest to the sun, the directions of their elongated paths, even the tilts of their orbits relative to the rest of the solar system. These similarities were too consistent to be mere coincidence. It's worth pausing to appreciate just how extraordinary this detective work really is. These objects appear as nothing more than faint dots of light, even in our most powerful telescopes. No surface features, no colors, no atmospheric details, just tiny specks crawling slowly across the star field. Yet from those subtle movements, astronomers can reconstruct entire orbital paths, calculate masses, and even infer the presence of objects they've never directly seen. To understand why these patterns matter, we need to look back at how our solar system formed. About 4.5 billion years ago, a rotating disk of gas and dust began to collapse under its own gravity. The sun ignited at the center, while the surrounding material slowly coalesced into planets. In the hot inner regions, only metals and rocky materials could survive, but farther out, beyond what astronomers call the frost line, water and other substances could freeze solid. This is why the giant planets formed in the outer solar system. They had access to vast amounts of ice, which allowed them to grow enormous and capture thick atmospheres of hydrogen and helium, but the process wasn't smooth or orderly. Young planets migrated inward and outward, their gravity flinging smaller objects into chaotic trajectories. Some debris was scattered to the very edges of the solar system, while other pieces were ejected entirely into interstellar space. The solar system we see today is the end result of that ancient chaos, and the scars of that violent history are still visible in the strange orbits of the most distant objects. It's like reading a story written in gravity and motion, deciphering events that happened billions of years before the first life appeared on Earth. Modern astronomy has also given us a broader perspective on planetary systems. Over the past few decades, we've discovered thousands of planets orbiting other stars. These exoplanets have revealed that planetary systems come in an astonishing variety of configurations. Some have giant planets hugging their stars in scorching hot orbits. Others contain multiple super-Earths packed into spaces smaller than Mercury's orbit around our Sun. One particularly intriguing discovery is that planets between the size of Earth and Neptune appear to be extremely common throughout the galaxy, yet our solar system seems to lack such a world, at least in its inner regions. This raises a fascinating question. Did our solar system simply never form such a planet? Or could one exist in the distant darkness beyond Neptune, too far away and too faint for us to have discovered it yet? The search for distant objects continues to push the boundaries of what's possible with current technology. Modern surveys use digital cameras that can photograph huge swaths of sky repeatedly, computers analyzing millions of images to identify tiny moving specks that might represent unknown worlds. Even so, the challenge is immense. An object hundreds of times farther from the Sun than Earth receives virtually no sunlight, making it incredibly difficult to spot against the cosmic background. But the absence of evidence isn't necessarily evidence of absence. Sometimes it simply means we haven't looked long enough, or carefully enough, or with instruments sensitive enough to reveal what's hiding in the shadows. The history of astronomy is filled with discoveries that were always there, waiting for the right technology or the right perspective to bring them into view. As our map of the solar system continues to expand, it becomes clear that the outer regions are not the empty wasteland we once imagined. They're rich with dwarf planets, icy asteroids, and vast populations of objects still being catalogued and studied. Each new discovery adds another piece to the puzzle, and with each piece comes the tantalizing possibility that something even larger might still be waiting in the darkness. This ongoing revelation changes how we think about our place in the cosmos. The solar system isn't a finished, closed system with well-defined boundaries. It's an open landscape that extends far beyond anything our ancestors could have imagined, a frontier that continues to surprise us with its complexity and richness. In a universe full of mysteries, perhaps the greatest mystery is the one that lies just beyond the edge of what we think we know. The outer reaches of our solar system hold secrets that unfold with the patience of geological time. Here, in this cosmic wilderness beyond Neptune, gravity works its slow magic on countless icy wanderers. These frozen remnants from our solar system's birth dance in orbits that stretch across thousands of years, carrying stories we're only beginning to decode. Picture this vast frontier, not as empty darkness, but as a sparsely populated realm where ancient objects follow paths carved by invisible forces. Some of these distant travelers, the ones astronomers call extreme trans-Neptunian objects, trace enormous elliptical journeys that carry them far from our sun's warmth, then back again in cycles longer than recorded human history. When scientists first began mapping these remote orbits in detail, something unexpected emerged from the data. Instead of pointing randomly in all directions, as you might expect from billions of years of chaotic interactions, many of these distant objects seemed to cluster together, their elongated paths, aligned in roughly similar orientations, like compass needles, all pointing towards some unseen magnetic north. This clustering presents a puzzle that speaks to something profound about how our universe works. Gravity, that most patient of cosmic forces, doesn't need dramatic strength to reshape entire worlds. Given enough time, even the gentlest gravitational whisper can guide massive objects into new configurations. In the outer solar system, where a single orbit can take millennia to complete, these subtle influences accumulate like interest in a cosmic savings account. Computer simulations revealed something fascinating when researchers tried to recreate this orbital clustering. Models that included only the known planets, the Sun, and the small bodies themselves couldn't maintain the observed patterns. The orbits would scatter randomly over time, defying what telescopes were actually seeing. Something seemed to be missing from the cosmic equation. Then came a remarkable possibility. What if a massive unseen planet lurked in the darkness beyond Neptune, one large enough to gravitationally shepherd these distant objects, yet too far away and too dim for our telescopes to spot directly? When astronomers added such a hypothetical world to their simulations, the mystery began to solve itself. A planet several times Earth's mass, traveling on a highly stretched orbit hundreds of times farther from the Sun than we are, could produce exactly the clustering patterns being observed. This indirect detective work has deep roots in astronomical discovery. Neptune itself was found through similar gravitational sleuthing, predicted from wobbles in Uranus's path before any telescope ever glimpsed it. The mathematical certainty led observers to point their instruments at a specific patch of sky, where they found the predicted world almost exactly where calculations said it should be. But cosmic history also whispers warnings about such indirect evidence. The 19th century search for Vulcan, a hypothetical planet proposed to explain Mercury's orbital quirks, ultimately led nowhere. Those anomalies were eventually explained not by another world, but by Einstein's revolutionary understanding of space and time itself. The story of this potential ninth planet began not with dramatic telescope discoveries, but with patterns emerging slowly from decades of patient observation. These distant regions guard their secrets carefully, revealing them like ancient manuscripts that must be decoded line by line. Objects move with glacial slowness in the outer darkness, where sunlight arrives as barely more than bright starlight. The gravitational hints accumulated gradually, building a case piece by piece rather than arriving as sudden revelation. Each new discovery of a distant object added another data point to the growing pattern, like archaeological fragments that slowly reveal the outline of some buried civilization. What makes this search particularly challenging is the sheer scale involved. If this hidden planet exists, it travels in an orbit so vast that its year could span 10,000 or even 20,000 of our own. At such distances, even a world several times larger than Earth would appear as nothing more than a faint point of light, easily lost among the countless stars that fill our telescope's view. The observational biases add another layer of complexity to this cosmic puzzle. Surveys of the outer solar system can't search everywhere equally, focusing on certain regions while leaving others largely unexplored. Objects become easier to detect when they're closer to the Sun in their long orbits, creating a selection effect that might influence what we think we're seeing. This selective vision raises profound questions about the nature of discovery itself. How much of what we observe reflects reality? And how much reflects the limitations of our instruments and methods? The universe may be full of wonders that remain invisible simply because we haven't learned how to look for them properly. The mathematical models that support this hidden planet's existence paint a picture of cosmic architecture operating on scales that challenge human intuition. A world massive enough to influence objects billions of miles away, yet so distant that it receives almost no heat from our sun. Its surface, if it exists, would be a realm of perpetual twilight, where temperatures hover near absolute zero. Such a planet would represent something like a cosmic fossil, a remnant from the early chaotic period when our solar system was still taking shape. Unlike the familiar worlds that orbit closer to the sun, this distant giant would have remained largely unchanged since its formation, preserving conditions from our cosmic neighborhood's violent youth. The search continues with the methodical patience that astronomy demands, each new observation adding to our understanding of these remote regions. Whether this hypothetical ninth planet actually exists remains an open question, one that speaks to the fundamental mystery of how much we still don't know about our own cosmic backyard. Observational bias creates a fascinating puzzle in astronomy. When telescopes scan the night sky, they naturally spot objects that shine brighter, objects that happen to be positioned closer to our sun. This creates a skewed sample of what we think we know about distant space. It's like trying to understand a forest by only looking at the trees closest to a streetlight. Some researchers point out that this bias might be creating phantom patterns, making us see alignments in clusters where none actually exist. The scientific method thrives on this kind of healthy skepticism. Hypotheses get proposed, then challenged, then tested again and again. Evidence slowly accumulates over years, decades, sometimes centuries. Each new discovery either strengthens or weakens our current understanding. It's a patient process, one that mirrors how gravity itself works, subtle and persistent. Out in the far reaches of our solar system, strange objects keep turning up. Some travel on orbits tilted at steep angles, almost standing upright compared to how planets normally move around the sun. These orbital paths seem nearly perpendicular to the flat disk, where most planets live. Computer simulations suggest that a massive distant planet could scatter objects into these unusual trajectories. The same gravitational shepherd that clusters some bodies together might fling others into wild, tilted orbits. Neptune's influence extends far into space, its gravity normally expected to disturb and scatter anything that wanders too close. Yet some distant objects maintain remarkably stable paths, almost as if they're avoiding Neptune's gravitational reach entirely. This hints at another massive presence out there, something helping to shape and protect these remote orbits. The effects remain subtle though, nothing dramatic or violent. The outer solar system operates like a quiet clockwork mechanism, its mysteries revealing themselves only through careful long-term observation. There's something deeply meditative about this branch of astronomy. Scientists gather data year after year, refining calculations, improving computer models, waiting patiently for patterns to emerge from the cosmic noise. The timescales involved dwarf human experience. Many of these distant objects take thousands, even tens of thousands of years to complete a single orbit around our sun. A human lifetime captures only the tiniest slice of their celestial dance. If this hypothetical ninth planet exists, it likely travels on such a vast orbit that it spends most of its time in the cold, dark outer regions of our solar system. Only occasionally would it swing closer to the sun, becoming slightly brighter, slightly easier to spot with our telescopes. Right now, it might simply be hiding in a patch of sky that hasn't been surveyed deeply enough. Or its faint light could be blending invisibly into the background stars. New telescopes promise to change this cosmic game of hide and seek. Advanced sky surveys are being designed to map the heavens more thoroughly than ever attempted before. These instruments will peer deeper into space, cataloging fainter objects, potentially revealing what's been hiding in the darkness all along. The search continues with renewed technological vigor. Until then, the evidence remains tantalizingly indirect. No clear visual confirmation, just a collection of gravitational clues. These whispers in the data speak of something massive and distant, something that influences its surroundings without showing itself directly. Gravity leaves its signature everywhere, creating patterns in motion, subtle fingerprints that trained eyes can learn to read. There's quiet beauty in this approach to discovery. The idea that something large and mysterious might announce its presence, not through brilliant light, but through gentle gravitational influence on distant neighbors. It's detective work on a cosmic scale, reading the evidence left behind in orbital mechanics and mathematical relationships. The question remains beautifully open, patiently waiting for resolution. A reminder that our solar system still holds secrets worth discovering. Orbits tell stories. Every path an object takes through space carries clues about its past, like footprints in cosmic dust that never quite fade away. When astronomers look at these paths, they're reading a history book, written in gravity and time. Most planets in our solar system are well-behaved children, following neat, circular paths that stay close to the same flat plane. You can predict where they'll be with stunning accuracy, sometimes centuries into the future, but venture beyond Neptune, and the orderly picture starts to unravel. Out there, objects follow strange, elongated paths that stretch impossibly far from the Sun before swooping back inward. These aren't your typical planetary orbits. They're more like cosmic boomerangs, disappearing into the darkness for millions of years at a time. Comets have always done this dance. They appear briefly in our inner solar system, put on a spectacular show, then vanish back into the outer darkness. Astronomers have known about this behavior for centuries, but something else started catching their attention, something much more puzzling. Certain distant objects weren't just following elongated paths, they were following eerily similar elongated paths. Their closest approaches to the Sun, their directions of travel, even the tilts of their orbital planes, all seemed to share mysterious patterns. This was deeply unusual. Imagine scattering a handful of marbles across a vast field, then coming back years later to find them arranged in neat rows. You'd naturally wonder what force had organized them. In space, objects should scatter randomly over time, unless something is guiding them. Picture those marbles again, but this time they're spinning wheels, rolling in different directions across an endless plane. Without any organizing force, you'd expect complete chaos, each wheel heading its own way with no discernible pattern emerging. Gravity can certainly act as an organizing force, but the known planets are simply too far away to strongly influence objects that wander hundreds of times Earth's distance from the Sun. Neptune has some reach, but its gravitational influence weakens dramatically with distance. Yet these distant objects were moving, as though something unseen was quietly shepherding their paths. Something was creating order where chaos should reign. Astronomers focus on specific measurements to understand these patterns. One crucial measurement is the argument of perihelion, which sounds complicated, but simply describes where an orbit's closest point to the Sun is oriented in space. If you mapped dozens of distant objects and found their closest approaches scattered in every possible direction, that would suggest randomness, exactly what you'd expect. But if many cluster in similar directions, it hints at a shared, invisible influence. That's precisely what researchers began noticing. Several extreme objects beyond Neptune showed arguments of perihelion that weren't randomly scattered, but clustered within a surprisingly narrow range. At first, this observation seemed tentative. Small samples can be misleading, like judging an entire forest by examining just a few trees. But as years passed and more objects were discovered, the clustering didn't disappear. If anything, it became harder to ignore. Another unusual feature involved the long axes of these orbits. These elongated paths seemed to point in similar directions through space, as though the objects were all avoiding some particular region or being guided along preferred cosmic highways. This led astronomers to ask a deceptively simple question. What kind of gravitational influence could maintain such patterns over billions of years? The answer required diving into computer simulations. When researchers modeled the outer solar system without any additional massive body, the clustered orbits gradually dispersed over time. Even weak gravitational interactions slowly scrambled the orientations, like a gentle breeze eventually scattering leaves. that had been raked into neat piles. But when a distant massive planet was added to these simulations, something remarkable happened. The clustering persisted. The hypothetical planet acted like a distant shepherd, its gravity gently nudging smaller objects into stable configurations that maintained their alignment across cosmic time. This shepherding effect didn't require violent collisions or dramatic close encounters. It worked slowly, patiently, over millions of years through a process called secular perturbation. In simpler terms, gravitational influence can gradually alter an orbit's orientation without dramatically changing its size or shape. It's a subtle process, like the way a river slowly carves a canyon. Individual water drops seem powerless against solid rock, but given enough time, subtle forces produce dramatic results. The puzzle had yet another intriguing piece. Some distant objects traveled on highly inclined orbits, tilted steeply relative to the plane where most planets orbit. A few even followed paths almost perpendicular to that plane, like cosmic rebels refusing to follow the crowd. Such extreme tilts are difficult to produce through interactions with known planets alone. It's like trying to flip a spinning coin, using only a gentle breeze from across the room. But simulations suggested that a distant massive body could scatter objects into these unusual orientations, creating a population of tilted orbits that matched what telescopes were revealing. The more data accumulated, the more this hypothesis of an unseen planet seemed capable of explaining multiple puzzling features simultaneously. The clustering of closest approaches, the alignment of orbital axes, the existence of steeply tilted paths, all could result from one hidden gravitational shepherd. Still, caution remained essential. Astronomy has witnessed apparent patterns before that later dissolved under closer scrutiny. Like mirages that disappear when you approach them, statistical illusions can be surprisingly convincing, especially when dealing with small numbers of very faint objects at the limits of detection. Observational bias presents a persistent challenge. Telescopes don't survey the sky uniformly. Some regions get observed more frequently, and objects are easier to spot when they're closer to the sun or located where background stars don't create confusion. These factors influence which objects get discovered and which remain hidden. If discoveries are biased towards certain sky regions, apparent clustering could arise even if the true distribution were completely random. It's like concluding that most people wear winter coats if you only survey during December. Researchers work carefully to account for these biases, analyzing survey methods and detection probabilities with mathematical precision. Some studies concluded that clustering remained significant, even after accounting for observational effects. Others argued the evidence was still inconclusive. This ongoing debate represents the normal, healthy heartbeat of science. Hypotheses get tested, challenged, refined, sometimes over many years or even decades. Truth emerges slowly, like a photograph developing in a dark room. Meanwhile, new discoveries continue adding pieces to this cosmic puzzle. One particularly intriguing object follows an orbit that carries it far beyond the Kuiper belt, with its closest approach to the Sun so distant that Neptune's gravity struggles to explain its trajectory. This object, along with similar wanderers, forms a group sometimes called inner Oort cloud objects. They occupy a transitional region between the relatively nearby Kuiper belt and the distant spherical halo of comets known as the Oort cloud. These transitional objects exist in a kind of gravitational no man's land, too far for Neptune to control effectively, yet not quite in the realm of the Oort cloud's gentle embrace. They're cosmic refugees, following paths that seem to remember influences we haven't yet identified. The search continues, each new discovery potentially confirming or challenging our understanding of what lurks in the outer darkness of our solar system. Perhaps there's a hidden planet out there, patiently orchestrating this cosmic dance, or perhaps we're seeing patterns where none truly exist, fooled by the inherent human tendency to find order in chaos. Either way, these distant objects remind us that our solar system still holds secrets. Even in our own cosmic neighborhood, mystery persists just beyond the reach of our telescopes, waiting in the cold darkness for the next breakthrough that might illuminate truth. The far reaches of our solar system hold objects that seem to dance to a rhythm we don't fully understand. These distant, icy bodies follow paths that shouldn't make sense, at least not based on what we thought we knew about how things move out there in the cold darkness beyond Neptune. When we look at these extreme trans-Neptunian objects, something strange emerges from their behavior. Many of them swing around the sun in ways that suggest they're being nudged or guided by forces we can't directly see. It's like watching marbles roll across a table and noticing they all curve in the same direction, even when there's no obvious reason why they should. Neptune, that distant blue giant, has enough gravitational pull to scatter most objects that wander too close. Yet some of these far-off bodies maintain orbits that keep them safely away from Neptune's influence, as if they know exactly where not to go. This kind of orbital precision doesn't happen by accident in the chaotic environment of space. The puzzle deepens when we consider how these objects might have ended up in such peculiar arrangements. Billions of years ago, when our sun was still part of a crowded stellar nursery, passing stars could have stirred things up out there. Their gravity might have yanked and twisted the paths of distant objects, setting up the strange patterns we see today. But stellar encounters from the distant past might not tell the whole story. Computer simulations suggest that something else could be at work, something that's still out there, still shaping these orbits through its gravitational influence. The mathematics point toward a world we've never seen, a planet moving through the outer darkness on its own, elongated path around the sun. This hypothetical planet wouldn't need to be particularly close to these smaller objects to affect them. Gravity works across vast distances, and even a planet hundreds of times farther from the sun than Earth could still reach out and organize the motions of nearby bodies. It's a bit like how a conductor can coordinate an entire orchestra without touching a single instrument. The concept of resonance plays a crucial role in understanding how such organization might work. When two objects orbit the sun, and their periods form simple mathematical relationships, something beautiful happens. Their gravitational interactions become synchronized, creating stable patterns that can persist for millions of years. Think of it like a cosmic dance, where the dancers never actually meet, but their movements are perfectly coordinated by invisible threads of gravity. Jupiter demonstrates this principle beautifully with the asteroid belt, where groups of space rocks follow paths that maintain specific timing relationships with the giant planet's orbit. A distant ninth planet could create similar resonant structures throughout the outer solar system. Objects caught in these gravitational sweet spots would find their motions locked into predictable patterns, their paths synchronized with the unseen world that governs their dance. The evidence for this hidden planet remains circumstantial, like trying to identify an animal by studying only its footprints. We can see the effects, the disturbances in the cosmic order, but the source remains frustratingly out of reach. Each new discovery of a distant object adds another footprint to examine, another clue to consider. Finding such a world directly would require extraordinary patience and precision. At the distances we're talking about, even a planet several times more massive than Earth would appear as nothing more than a faint dot of reflected sunlight. It would be thousands of times dimmer than Neptune, barely distinguishable from the countless stars that fill the background of space. The search involves comparing photographs taken months or years apart, looking for the tiniest shift that might reveal a planet's slow crawl across the sky. At such vast distances, even a world racing around the sun at tremendous speeds would appear to barely creep along, like watching the hour hand of a clock move. This kind of detective work speaks to something profound about human curiosity and persistence. We've learned to read the language of gravity itself, to interpret the subtle signatures that invisible worlds leave in the motions of distant objects. It's remarkable that we can even contemplate the existence of a planet we've never seen, based purely on mathematical relationships and all beginnings. The outer solar system remains a frontier where our knowledge grows thin and mysteries multiply. Even after centuries of astronomical observation, we're still discovering that our cosmic neighborhood holds surprises. The possibility that a substantial world has been hiding out there all along, undetected and unsuspected, reminds us how much we still don't know about our own celestial backyard. As astronomers continue their patient work, mapping the orbits of ever more distant objects, they're essentially conducting an archaeological dig through the architecture of space itself. Each measurement refines our understanding. Each discovery either strengthens or challenges the emerging picture of how the outer solar system is organized. The question isn't just whether this planet exists, but what it might be like if it does. In that realm of perpetual twilight, where the sun appears as nothing more than the brightest star in a black sky, temperatures would hover near absolute zero. Any world out there would be a frozen, alien place, perhaps shrouded in thick atmospheres of hydrogen and helium, or maybe covered in exotic ices we can barely imagine. Yet, even in such hostile conditions, this distant world, if it exists, would be playing a crucial role in shaping the solar system we call home. From hundreds of billions of miles away, it would be conducting its own silent orchestra, organizing the paths of countless smaller bodies through nothing but the patient, persistent pull of gravity across the vast emptiness of space. Detection without direct observation happens constantly in our daily experience. The warmth from sunlight touches your skin long before you glance upward at its source. Footsteps echo from another room, revealing someone's presence before any visual confirmation arrives. We infer reality through effects, rather than direct sight. This same principle drives many of astronomy's greatest breakthroughs. Throughout scientific history, the most profound discoveries often began with subtle hints, rather than clear images. Small deviations in expected patterns, gentle influences that shouldn't exist, mysterious tugs pulling at known objects. These whispers from the cosmos frequently reveal truths that telescopes cannot yet capture directly. Gravity excels at exposing hidden celestial bodies. Every object possessing mass creates gravitational pull, regardless of distance or apparent brightness. That pull might seem impossibly weak, nearly imperceptible to our instruments. But across vast stretches of time, gravitational influence leaves unmistakable traces in other bodies' movements. Orbits begin shifting in unexpected ways. Paths bend slightly from their predicted courses. Patterns emerge that make no sense if only known objects were present. Astronomers sometimes describe this phenomenon as feeling a planet before seeing it. Not through physical touch, obviously, but through recognizing gravitational presence in surrounding objects' behavior. Neptune's discovery followed exactly this process. Astronomers noticed irregularities in Uranus's orbit that demanded explanation. Mathematical calculations pointed toward an undiscovered world tugging at the known planet. Only after determining where this hidden influence originated did telescopes finally spot Neptune itself. Countless exoplanets around distant stars revealed themselves through similar methods. Astronomers observed tiny wobbles in stellar motion caused by unseen planetary companions. These worlds remained invisible, lost in their star's overwhelming glare. Yet their gravitational signatures betrayed their existence completely. Planet 9, if it exists, represents this detection principle on an extraordinary scale. The evidence doesn't come from observing a single object's unusual behavior. Instead, multiple distant bodies collectively point toward a common gravitational source. Imagine noticing leaves on a pond, all drifting in eerily similar patterns, then realizing some invisible current must be guiding their movement. This hypothetical world would dwarf Earth several times over. Current estimates suggest it might rival Uranus or Neptune in size, though probably somewhat smaller than those ice giants. We're not discussing some tiny asteroid hiding in darkness. This would be a substantial planet, gravitationally dominating its entire region of space across tremendous distances. Yet, despite such impressive size, this world could remain completely hidden, simply due to extreme distance. Understanding this invisibility requires considering how light and distance interact in space. Any object's brightness depends on two crucial factors. First, how much sunlight actually reaches that object. Second, how much reflected light travels back toward Earth. Both factors diminish dramatically as distance increases. A planet positioned 10 times farther from the Sun than Earth receives only 1/100th as much sunlight. At 100 times Earth's distance, incoming sunlight becomes 10,000 times weaker. That feeble reflected light must then traverse the entire return journey to Earth, growing fainter still during its cosmic voyage. At distances measuring several hundred astronomical units, even substantial planets become barely distinguishable points of light. Worlds that might appear vibrant and colorful, up close transform into cold, dim specks, barely brighter than background stars. Movement adds another layer of concealment. Objects at such extreme distances crawl across the sky with glacial slowness. From our perspective, their motion might take months or years to become detectable. Most astronomical surveys focus on faster-moving objects like asteroids or closer trans-Neptunian bodies. A planet creeping along at such a gradual pace could easily evade notice. Therefore, absence of direct observation doesn't necessarily indicate absence of existence. The object might simply be too faint, too slow, and located in sky regions that haven't received sufficiently deep searches yet. This explains why astronomers rely heavily on indirect evidence. They hunt for gravitational fingerprints, orbital patterns that known influences cannot explain alone. The Planet 9 hypothesis proves compelling, partly because it simultaneously explains several different observations: the clustering of distant orbits, the existence of highly tilted objects, the presence of bodies that maintain distance from Neptune. All these phenomena fit naturally into computer simulations that include a distant massive planet. Multiple clues scattered throughout the outer solar system seem to point toward the same invisible source. Alternative explanations certainly exist. Some scientists propose that clustering might result from collective gravitational effects among many smaller bodies, rather than one large planet. Others suggest observational biases could still influence data in subtle, unrecognized ways. These considerations deserve serious attention. Science advances by testing ideas from every conceivable angle, searching for weaknesses, refining models, gathering additional evidence. Healthy skepticism drives progress more effectively than blind acceptance. Nevertheless, the Planet 9 possibility remains compelling, partly because it aligns with broader understanding of planetary system formation. When astronomers study other stars, they frequently discover planets larger than Earth but smaller than Neptune. These worlds, sometimes called super-Earths or mini-Neptunes, appear remarkably common throughout the galaxy. Our solar system seems to lack such intermediate-sized worlds in its inner regions. Mercury, Venus, Earth and Mars are all relatively small. Beyond them lie the gas giants, creating a puzzling size gap between Earth and Neptune. This absence has mystified astronomers for years. Why does our solar system apparently lack the galaxy's most common planetary type? One possibility involves early formation dynamics. Perhaps such a planet did form here originally but got scattered outward during the chaotic period when giant planets were migrating through the system. Interactions among Jupiter, Saturn, Uranus and Neptune could have flung a fifth large planet into a distant orbit, where it continues circling slowly and silently. Computer simulations of planetary formation sometimes produce exactly these results. Some models show additional planets getting ejected entirely, becoming rogue worlds drifting between stars. Others demonstrate planets remaining gravitationally bound while being pushed into distant, elongated orbits. If Planet 9 exists, it might represent a survivor from that tumultuous early era, a relic from when the solar system was far more crowded and chaotic than today's relatively stable configuration. Imagining such a world transforms our entire conception of the solar system. Instead of a compact planetary family clustered near the Sun, we begin recognizing a vast system extending deep into darkness. Distant members move on timescales far exceeding human lifetimes. A year on such a planet might last 10,000 Earth years or longer. Seasons, if they occur at all, would change so gradually that no civilization could observe complete cycles. The Sun would appear as a brilliant star, bright enough to cast shadows but insufficient to provide meaningful warmth. Surface temperatures would hover near absolute zero, perhaps only a few dozen degrees above that ultimate cold limit. Any atmosphere would likely be thin or completely frozen. The landscape might be covered in exotic ices, methane, nitrogen, carbon monoxide, substances that exist as gases on Earth but become solids under such frigid conditions. Yet, even in this remote environment, fundamental physics continues operating. Gravity shapes orbits according to the same laws. Heat flows outward from planetary interiors, though extremely slowly. Chemical processes persist, albeit at nearly imperceptible rates. This represents a quiet form of existence, utterly removed from the warmth and activity characterizing inner solar system worlds. Not devoid of interest or complexity, but operating according to different rhythms entirely. Something profoundly humbling emerges from considering that such a world might exist within our own solar system. Not in some distant galaxy, but in our immediate cosmic neighborhood, unseen yet exerting measurable influence on observable objects. This possibility reminds us that exploration remains unfinished. Even familiar territory can conceal surprises. Maps can still contain blank regions awaiting discovery. The universe consistently proves more mysterious and wonderful than our current understanding suggests. Astronomers continue searching using increasingly sophisticated telescopes that scan enormous sky areas simultaneously. The Vera Rubin Observatory, for example, should detect vast numbers of distant objects, potentially providing data needed to confirm or eliminate Planet 9's existence. Until definitive evidence arrives, the case remains circumstantial, a story told through gravitational interactions rather than direct images. Perhaps this uncertainty makes the mystery even more captivating. There exists quiet elegance in discovering worlds not through direct observation, but by recognizing the gentle ways they influence their surroundings. Subtle signatures left in distant bodies' motions create a cosmic detective story where gravity serves as both the evidence and the investigative tool. When you peer out past Neptune, something remarkable happens to our solar system. The orderly arrangement of planets, those familiar worlds circling in their predictable paths, slowly gives way to something entirely different. Out there, floating in the cold darkness, lies a vast collection of icy remnants from the birth of our cosmic neighborhood. For most of human history, we had no idea this region even existed. Ask any astronomer from a century ago what lay beyond Neptune, and they'd probably mention Pluto, then wave their hand toward empty space. The tools simply weren't powerful enough to reveal what was actually there, waiting patiently in the darkness. Distance has a way of hiding secrets. When objects are billions of kilometers away and reflect barely any sunlight, they become nearly invisible. It's not that they aren't there, it's just that finding them requires incredible patience and technology that didn't exist until recently. The story begins, as many scientific stories do, with someone making an educated guess decades before anyone could prove it. Back in 1951, an astronomer named Gerard Kuiper had a hunch. He figured that when our solar system was forming, not everything got swept up into planets. Some material, he thought, probably got left behind in the outer reaches, like cosmic leftovers from a massive construction project. For 40 years, this remained just an idea. Then, in 1992, two astronomers finally spotted something. A small, dark object drifting far beyond Pluto's orbit. They gave it the rather unpoetic name 1992 QB1, but this little chunk of ice and rock represented something profound. Pluto wasn't alone out there, after all. Once astronomers knew what to look for, more objects started appearing. First a few dozen, then hundreds, now thousands. Each one a small world in its own right, ranging from city-sized chunks to objects hundreds of kilometers across. We call this region the Kuiper Belt, and it stretches from about Neptune's distance out to roughly 50 times Earth's distance from the Sun. To put that in perspective, imagine Earth's orbit as a small circle. The Kuiper Belt would be like a wide ring starting 30 times farther out and extending 20 times beyond that. Even light from the Sun takes hours to reach these distant worlds, arriving weak and cold. Despite containing thousands of objects, this region isn't crowded at all. If you could somehow travel through it, you'd mostly see empty space. The icy bodies are typically millions of kilometers apart from each other. It's more like islands scattered across a vast ocean than rocks tumbling through a narrow canyon. These frozen worlds represent something special, though. They're essentially time capsules from 4.5 billion years ago. When our solar system was young, a massive disk of gas and dust surrounded the sun. Most of this material clumped together to form planets, but the objects in the Kuiper Belt never grew large enough to dominate their neighborhoods. They remained small, preserving the original chemistry and structure from those ancient times. Pluto itself, once considered the 9th planet, is now understood as simply the largest member of this distant population. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more complex than anyone expected. Heart-shaped plains of nitrogen ice, towering mountains, and signs of geological activity. Even at those frigid temperatures, with sunlight 1,000 times dimmer than Earth receives, dynamic processes still shape these worlds. Pluto isn't unique either. Several other dwarf planets call the Kuiper Belt home. Eris, Haumea, and Makemake each have their own characteristics. Some spin so rapidly they've been stretched into elongated shapes. Others have small moons orbiting them. A few might even have thin atmospheres that freeze solid and then evaporate again during their centuries-long trips around the sun. These discoveries have gradually transformed how we think about our solar system's architecture. The outer regions aren't empty voids punctuated by occasional lonely worlds. They're complex, structured environments shaped by billions of years of gravitational interactions and cosmic accidents. The Kuiper Belt serves another important function too. It's the source of many comets that occasionally visit the inner solar system. These icy wanderers get nudged inward by gravitational interactions, eventually developing those spectacular glowing tails when they approach the sun. In essence, the Kuiper Belt acts like a slow-motion reservoir, continuously supplying new visitors to our neighborhood over millions of years. As astronomers studied more of these objects, they noticed something interesting about their orbits. Some follow nearly circular paths, locked in gravitational resonances with Neptune. Pluto, for instance, completes exactly 2 orbits for every 3 of Neptune's, a cosmic dance that's been going on for billions of years and ensures the 2 worlds never get too close. Other objects have more eccentric orbits, suggesting more violent histories. Some appear to have been scattered outward by close encounters with Neptune long ago. These scattered disk objects can travel hundreds of times Earth's distance from the Sun before swinging back inward, taking thousands of years to complete a single orbit. The Kuiper Belt isn't uniform either. It has structure, regions where objects cluster together, and gaps where few are found. Much of this organization can be explained by Neptune's gravitational influence during the early days when the giant planets were migrating to their current positions. But not all of it. Some objects orbit so far out and on such unusual paths that Neptune's gravity can't explain their motions. Take Sedna, for example. This world travels nearly 1,000 times Earth's distance from the Sun at its farthest point. Even when it's closest to the Sun, it remains far beyond Neptune's gravitational reach. What could have placed Sedna on such an extreme orbit? Perhaps a passing star billions of years ago, or gravitational interactions with other massive objects during the solar system's chaotic youth. Or perhaps something large still lurks in the outer darkness, slowly influencing these distant worlds over geological timescales. This is where the Kuiper Belt connects to one of astronomy's current mysteries. Some of the most distant objects show subtle patterns in their orbits, alignments that seem too organized to be coincidental. Their elongated paths point in similar directions, and their orbital orientations cluster in ways that randomness alone can't easily explain. These aren't dramatic effects. No object is being violently perturbed. Instead, there's a gentle sense that something massive might be shepherding these distant worlds, maintaining patterns that should have dispersed long ago if left to purely random interactions. Studying these remote objects requires extraordinary patience. They're so faint that detecting them pushes telescopes to their limits. Determining their orbits accurately requires observations spanning many years. sometimes decades. A single observation captures only a tiny fraction of an orbital path that might take millennia to complete. There's something almost meditative about this kind of work. The gradual accumulation of data points, the slow refinement of orbital calculations, the patient wait for patterns to emerge. Astronomy often operates on these extended timescales, where understanding develops not over months, but over decades of careful observation. At the distances where these objects orbit, everything moves incredibly slowly, where Earth completes its yearly journey in 365 days. Objects in the outer Kuiper belt might take centuries for a single orbit. The most distant known objects have orbital periods longer than recorded human history. This leisurely pace means that gravitational influences can act over extraordinarily long time spans. Changes that would be obvious in the inner solar system unfold almost imperceptibly in these remote regions. If a distant massive planet exists, its effects wouldn't be immediately obvious. Instead, they would reveal themselves gradually through the collective behavior of many objects over geological timescales. The scale of these orbits puts our own cosmic neighborhood in perspective. Earth's comfortable distance from the Sun, our familiar seasonal cycle, our predictable year, all exist in what amounts to the very inner circle of a much larger gravitational system. Even Neptune's 165-year orbit seems brief compared to the timescales operating in the Kuiper belt's outer fringes. Scientists sometimes describe the Kuiper belt as a frozen archive, preserving conditions from the solar system's formation. But it's also a dynamic environment, slowly evolving through gravitational interactions, occasional collisions, and rare perturbations from passing stars, and perhaps somewhere in the outer darkness, influenced by the gravity of an undiscovered world. The search continues. Astronomers survey the sky methodically, looking for faint points of light that move just enough to reveal their true nature. Each new discovery adds another piece to the puzzle, another orbit to calculate, another clue about how our planetary system formed and continues to evolve. What once seemed like empty space beyond Neptune has revealed itself as a rich, complex frontier. The Kuiper belt has become one of the most important regions for understanding our cosmic origins and possibly for discovering that our solar system still holds secrets we never imagined. The outer reaches of our solar system hold secrets that reveal themselves only through the language of mathematics and motion. Beyond Neptune, where sunlight barely whispers across frozen worlds, astronomers have been watching distant objects trace their ancient paths through space. Each orbit tells a story, and sometimes when you collect enough stories, a larger truth begins to emerge. Imagine trying to understand the behavior of leaves floating on a pond by watching them drift one by one. At first, their movements seem random, scattered by invisible currents. But if you observe long enough, patterns start to appear. Some leaves cluster together, others avoid certain areas entirely. Eventually, you realize that something beneath the surface, something you cannot see directly, is guiding their motion. This is essentially what happened in the cold darkness beyond Neptune. Astronomers studying distant objects called extreme trans-Neptunian objects noticed something peculiar about their orbits. These are bodies that venture so far from the Sun that they never experience Neptune's direct gravitational embrace. They should behave randomly, their orbital orientations scattered in all directions like compass needles with no magnetic north to guide them. But that's not what observers found. Instead, several of these distant wanderers seem to share something unexpected. Their closest approaches to the Sun, their perihelia, pointed roughly in the same direction. Their elongated paths appeared aligned, as if following invisible highways carved through the cosmos. The significance of this discovery becomes clearer when you understand how orbits work in three-dimensional space. An orbit isn't just a simple loop around the Sun. It has an orientation, a direction where its longest axis points, a tilt compared to the flat plane where most planets travel. If gravitational forces acted randomly on these distant bodies, their orientations should point everywhere, scattered across all possible directions, like arrows shot blindfolded. Random processes, after all, tend to produce random results. It's one of the fundamental principles that governs how things behave when no organizing force is present. that the outer solar system was showing signs of organization, and that demanded an explanation. At first, only a handful of objects displayed this clustering behavior. Small numbers can be deceiving, though. Coincidences happen all the time in astronomy. Sometimes patterns appear where none truly exist, like seeing faces in clouds or animals in constellations. Astronomers understand this tendency and resist drawing conclusions too quickly. But as more distant objects were discovered and their orbits calculated with increasing precision, the clustering persisted. It wasn't perfect alignment. Nature rarely produces perfect patterns, but the similarity was striking enough to capture scientific attention. Michael Brown and Konstantin Batygin decided to investigate whether this clustering could arise naturally from the gravitational influence of known planets alone. They created computer simulations modeling the outer solar system over vast periods of time. These digital universes included the Sun, the giant planets, and populations of small distant bodies, all interacting according to the laws of gravity. Over millions and billions of simulated years, something interesting happened. The orbits in these models tended to spread out randomly. The clustering observed in real life did not persist in their simulations. This suggested that something was missing from their model, some influence they hadn't accounted for. So they tried adding a hypothetical planet to their simulations, a world far beyond Neptune, with several times Earth's mass and an orbit stretching hundreds of astronomical units from the Sun. The results were remarkable. With this additional planet included, the clustering of distant orbits could be maintained over long time scales. The simulated objects began behaving in ways that closely resembled real observations. It wasn't proof, of course, but it was a compelling clue that something massive might be lurking in the outer darkness, gently shepherding these distant objects into their observed patterns. There was another, intriguing aspect to consider. Some distant objects had orbits that were not just aligned, but anti-aligned with the hypothetical planet's path. Their elongated orbits pointed in directions that would keep them far from the planet itself, actively avoiding close encounters. This might sound counterintuitive at first. How could a planet influence objects without pulling them directly toward it? The answer lies in the subtle complexities of orbital mechanics. Over long periods, gravitational interactions can create stable configurations where objects avoid close approaches, settling into patterns that minimize disruptive encounters. Think of it like dancers on a crowded floor, each finding rhythms that keep them from colliding, adjusting their steps in response to others around them. A distant planet could act as a kind of cosmic conductor, shaping the orbits of smaller bodies through gentle, persistent gravitational nudges. Still, caution remained necessary. Observational bias posed a serious concern. Telescopes don't search the sky evenly. Some regions get studied more frequently than others, and objects are easier to detect when they're closer to the Sun or located where background stars don't interfere. If most discoveries occurred in certain sky regions, it could create an illusion of clustering, even if the true distribution were completely random. Researchers analyzed the survey methods used to discover these objects. They examined which parts of the sky had been searched, how detection probabilities varied, and whether clustering could be explained by observational bias alone. The results sparked debate. Some studies concluded that clustering remained statistically significant even after accounting for biases. Others argued that sample sizes were still too small for certainty. This ongoing debate represents an important part of the scientific process. Extraordinary claims require careful scrutiny, and astronomers understand how easily patterns can mislead human perception. We're naturally inclined to see order where none exists, to connect dots that shouldn't be connected. Meanwhile, new discoveries continued adding weight to the mystery. Additional, extreme trans-Neptunian objects were found, and many fit the established pattern. The clustering didn't disappear as sample sizes grew larger. If anything, it became more intriguing. Another curious feature emerged as well. Some distant objects were found traveling on highly inclined orbits, tilted steeply relative to the solar system's main plane. A few even had orbits nearly perpendicular to that plane, standing almost upright like spinning coins compared to the flat disk where planets normally travel. Such extreme tilts are difficult to produce through interactions with Neptune alone. Simulations suggested that a distant massive planet could scatter objects into these unusual orientations, while simultaneously maintaining the clustering behavior of others. Multiple pieces of evidence, each puzzling individually, began forming a coherent picture when considered together. Yet, the picture remained incomplete. Astronomers didn't know where such a planet might be located. They couldn't determine its exact mass or orbital path. They only knew that certain patterns in distant object motions seemed easier to explain if such a world existed. There's something quietly fascinating about this kind of investigation. It doesn't unfold dramatically or suddenly. Instead, it advances slowly through careful measurements and patient analysis. Through years of observations and countless hours of computer modeling, it reminds us that science often progresses not through sudden flashes of inspiration alone, but through persistence and meticulous attention to detail. The clustering mystery also highlights how much of our solar system remains unexplored. The region beyond Neptune is vast, far larger than the inner planetary neighborhood we know well. Even with modern telescopes, only a small fraction of its objects have been discovered. Thousands, perhaps millions of distant bodies trace orbits we know nothing about. Each new discovery has potential to refine our understanding, to confirm or challenge existing theories, to reveal patterns that were previously invisible. Somewhere among those faint points of light, there may be clues that bring us closer to answering fundamental questions about our cosmic neighborhood's architecture. One striking aspect of the clustering phenomenon is how delicate it appears to be. The gravitational influence required to maintain such patterns doesn't need to be overwhelming. It only needs to be consistent, acting over millions of years, gently guiding smaller bodies' orbits like a patient gardener shaping a hedge. This reveals one of the quiet truths of celestial mechanics. Given enough time, even small forces can shape entire systems' architecture. A planet hundreds of astronomical units away could influence objects that never come close to it, simply through gravity's long, slow pull across the cosmic void. It's also a reminder of how interconnected everything in our solar system really is. No world exists in isolation. Every mass, no matter how distant, contributes to the gravitational symphony that orchestrates planetary motion. Even the smallest perturbations, accumulated over geological timespans, can leave their signatures in the orbits of distant worlds. As astronomers continue studying the clustering of distant orbits, they refine their models constantly, testing different scenarios, adjusting parameters, comparing results with observations. Some models suggest that a planet between 5 and 10 times Earth's mass, traveling on a highly elongated orbit, could reproduce many observed features. But models aren't reality. They're tools, ways of exploring possibilities and testing our understanding against what we observe. The ultimate test will be direct observation, either detecting the planet itself or accumulating enough evidence to definitively confirm or rule out its existence. For now, the clustering mystery remains one of planetary science's most intriguing puzzles. It's a story told through motion rather than light, through mathematical patterns rather than direct images. And as we consider what kind of world could produce such far-reaching effects, we're drawn deeper into questions about the true architecture of our cosmic home. Mathematics often reveals what our eyes cannot see. When astronomers study the distant edges of our solar system, they notice something peculiar. Objects that should move randomly don't. Instead, these icy worlds cluster together in ways that defy explanation. The outer solar system holds secrets that numbers decode better than telescopes. Equations whisper about invisible forces, about gravitational tugs from something massive, something hidden. These mathematical clues don't show us colors or surfaces, but they reveal influence, patterns that shouldn't exist unless something unseen pulls the strings. Distant objects beyond Neptune behave strangely. Their orbits cluster in ways that known planets cannot explain. Jupiter, Saturn, Uranus, Neptune, none of them can account for what astronomers observe. These far-off worlds follow paths that are too similar, too organized, too stable for coincidence. Computer simulations become time machines, running for millions of imaginary years. Scientists watch digital solar systems evolve, observing how orbits change over vast timescales. Without an extra planet, the clustering falls apart. Orbits spread randomly, just as physics predicts they should, but when researchers add a hypothetical world to their models, something remarkable happens. The clustering remains stable. The patterns match what telescopes actually see. Mathematics begins to whisper, rather than merely suggest, this hidden world, if it exists, must be precisely the right size. Too small, and its gravitational pull proves too weak, too large, and it creates disturbances we should have noticed by now. The calculations point towards something roughly 5 to 10 times Earth's mass. Such a planet would dwarf our world, yet remain much smaller than the gas giants. Its orbit stretches impossibly far from the Sun, hundreds or even thousands of times Earth's distance. A single trip around our star might take 15,000 years. Consider that time frame for a moment, when this world last occupied its current position. Humans lived in caves. We carved tools from stone, painted on rock walls, knew nothing of agriculture or writing. Civilizations have risen and fallen, while this distant planet crawled along just one portion of its orbit. The planet's path tilts away from the flat disk where most worlds travel. This tilt explains other mysteries, why some distant objects follow steeply angled paths that seem to ignore the solar system's usual rules. These calculations prove remarkably sensitive. Tiny changes in mass or distance create vastly different outcomes over millions of years. Researchers run thousands of simulations, adjusting variables like musicians, tuning instruments. The right combination produces gravitational harmony that matches observations. Each new discovery of distant objects tests these models. Some simulations gain support, others get discarded as reality proves them wrong. This process moves slowly, but methodically, like detective work, following clues across cosmic distances. Stability presents another puzzle. Any planet still orbiting today must have survived for over 4 billion years. It cannot have been ejected into deep space or pulled into a collision course with other worlds. The simulations suggest this survival is possible, provided the planet stays far from the giant planets most of the time. How did such a world reach such a distant orbit? Perhaps it formed closer to the Sun, then got scattered outward during the solar system's chaotic youth. In those early days, planets migrated dramatically, interacting violently with each other and countless smaller bodies. Computer models show these ancient interactions, flinging worlds into distant orbits. Some planets escape entirely, becoming rogues drifting between stars. Others remain bound to the Sun, traveling on stretched, elongated paths. Planet 9 might be such a survivor, pushed outward long ago, but never quite breaking free. Alternatively, it might have formed where it sits now, slowly gathering material in the solar system's distant reaches. This scenario proves more challenging because the outer regions contain less raw material for planet building. The mathematical evidence grows stronger with each new discovery, yet direct detection remains elusive. This hidden world, if real, reflects almost no sunlight and moves incredibly slowly across the sky. Finding it requires knowing where to look, a cosmic needle in an astronomical haystack. The search continues, guided by ever-improving simulations and increasingly precise observations. Perhaps one day a telescope will capture that faint dot of light, transforming mathematical possibility into photographic reality. Until then, the equations keep whispering their secrets, describing a world that may orbit in darkness, shaping the solar system through pure gravitational influence. The story reminds us how much remains unknown about our cosmic neighborhood. Even after centuries of discovery, the solar system still holds mysteries, still challenges our understanding. Mathematics serves as our guide through this darkness, revealing invisible worlds through the language of numbers and the patient work of simulation. The outer reaches of our solar system hold mysteries that challenge everything we thought we knew about planetary formation. When astronomers look at the sparse material scattered beyond Neptune's orbit, they face a puzzle. The density of matter out there seems far too thin, too scattered, to have assembled into anything substantial during the early days of our solar system. Yet some researchers wonder if, under very specific conditions, planet building might still be possible in those distant realms. The mathematics suggests it's unlikely, but not impossible. There's an even stranger possibility, though, one that sounds almost like science fiction. What if a massive planet didn't form out there at all, but instead was stolen from another star? During the Sun's youth, it likely lived in a crowded stellar nursery, surrounded by other young stars and their developing planetary systems. In such chaotic environments, gravitational interactions can become incredibly complex. Planets can be ejected from their home systems, sent wandering through space. Others might be captured by passing stars, pulled into new orbits around unfamiliar suns. The odds of such cosmic theft are vanishingly small, but the universe has had billions of years to roll the dice. What seems impossible becomes merely improbable when you consider the vast scales of time and space involved. Mathematics alone cannot tell us which origin story is correct. It simply whispers that something massive could be hiding out there, influencing the dance of smaller worlds through invisible threads of gravity. The search for this hypothetical world presents unique challenges. Rather than scanning the entire sky randomly, astronomers can use orbital mechanics to narrow their hunt. By studying how distant objects cluster and align, they can identify regions where a hidden planet is more likely to lurk. It's like using footprints to guess where someone might be hiding, even when you can't see them directly. But even with these mathematical clues, the search remains monumentally difficult. A planet at hundreds of astronomical units from the Sun would appear as nothing more than a faint point of light, barely brighter than the most distant stars. Its motion would be glacially slow, taking months or years of careful observation to detect any shift against the background of space. This situation isn't entirely new in astronomy's history. Neptune was discovered through pure calculation before anyone actually saw it. Exoplanets were detected through the subtle wobbles they cause in their parent stars long before we could photograph them. Gravitational waves were predicted by Einstein a century before our instruments became sensitive enough to feel space itself rippling. There's something deeply reassuring about this pattern. The universe, despite its vastness and complexity, follows rules that human minds can understand. Patient mathematics can reveal hidden truths, pointing the way toward discoveries that await future observation. It suggests an underlying order to reality, a cosmic logic that rewards careful thinking. Yet mathematics is not infallible. Models can be incomplete, built on flawed assumptions or misinterpreted data. The history of science is littered with promising hypotheses that later crumbled under scrutiny. This is why researchers continue probing the Planet 9 hypotheses from every conceivable angle, searching for alternative explanations and refining their techniques. Still, the possibility remains captivating. Imagine a world several times more massive than Earth, following a slow, elongated orbit through the outer darkness. Its year would last longer than all of recorded human history. Sunlight would be little more than a dim glow, barely distinguishable from other bright stars. Despite its remoteness, such a planet would leave unmistakable signatures in the architecture of our solar system. Through gravity alone, it would shape the paths of countless smaller objects, creating patterns that persist across geological time. It's a reminder that influence doesn't always require proximity. Sometimes the most distant forces shape our local reality in ways we're only beginning to understand. If such a world exists, what might it actually be like? The question of size becomes crucial here, because mass determines gravitational influence. A small object, even hundreds of kilometers across, simply wouldn't have enough gravity to create the orbital patterns astronomers observe. The clustering of extreme trans-Neptunian objects requires something far more substantial. But the planet can't be too massive either. Something comparable to Jupiter or Saturn would create gravitational chaos throughout the outer solar system. Its effects would be obvious, impossible to miss. So astronomers have been looking for a middle ground, something massive enough to matter, but subtle enough to remain hidden. Computer simulations suggest that a planet between 5 and 10 times Earth's mass could produce the observed effects. That places such a world in a fascinating category. At that scale, gravity becomes powerful enough to capture thick layers of gas and ice during formation. The result would be what astronomers call a mini Neptune or super-Earth. These intermediate-sized planets appear to be incredibly common throughout the galaxy. In fact, they might be the most typical kind of world in the universe. Yet our own solar system seems to lack such a planet in its inner regions. If Planet 9 exists, it would fill that gap, representing a missing piece of our cosmic neighborhood. The irony is striking. The most common type of planet in the galaxy might be hiding in our own backyard, so distant and cold that we've never noticed it. It would be a world of extremes, where temperatures hover near absolute zero, and storms, if they exist at all, would rage in near total darkness. Such a planet might have moons, perhaps captured asteroids or remnants from the solar system's formation. It might even have rings, though they would be invisible from Earth, detectable only through their subtle effects on radio signals or reflected starlight. The surface, if it has one beneath layers of atmosphere, would be a frozen wasteland where exotic ices never melt. This search represents more than just planetary astronomy. It touches on fundamental questions about how solar systems form and evolve. If Planet 9 exists, it would force us to revise our understanding of the early solar system's history. It would suggest that planetary formation is more complex and varied than current theories predict. The hunt continues, using ever more sophisticated techniques and instruments. Each new survey covers more of the sky with greater sensitivity. Each computational model becomes more detailed and realistic. The mathematics grows more refined, the predictions more precise. Whether Planet 9 exists or not, the search itself advances our understanding of the cosmos. It pushes the boundaries of observational astronomy and forces us to confront the limits of our knowledge. In the darkness beyond Neptune, we're not just looking for a planet. We're exploring the edge of the known world, probing the shadows where mathematics meets mystery. The composition of a distant world tells us everything about its character. When we think about a planet weighing 5 to 10 times what Earth weighs, we're imagining something fundamentally different from our rocky home. Out there in the cold depths, beyond Neptune's reach, materials behave in ways that seem almost alien to us. Rock becomes less important, ice becomes the foundation of entire worlds. Water ice, methane ice, ammonia ice. These substances that barely exist on Earth's surface become the building blocks of something massive and enduring. The very idea of such composition forces us to reconsider what we mean by solid ground. On Earth, we stand on rock formed by geological processes spanning billions of years. But imagine standing, if you could, on a world made largely of frozen volatiles. The ground beneath your feet would be ice harder than steel, carved by processes we can barely comprehend. Hydrogen and helium might wrap this frozen core in a thick envelope, creating layers upon layers of atmosphere that dwarf anything we know. Temperature becomes a character in this story, not just a measurement. -200 degrees Celsius transforms everything we understand about weather, about atmosphere, about the very notion of seasons. At such temperatures, gases we breathe freely become solid. The air itself, if we can call it that, moves like thick syrup, carrying frozen particles that would seem like dust made of materials that are liquid or gas on Earth. Clouds of frozen methane drift through skies so cold that thinking about them makes our own winter seem tropical. The light, reaching such a distant world, carries its own philosophical weight. Sunlight, that fundamental force that drives almost everything we know about life and weather and seasons, becomes nothing more than bright starlight. The sun, that massive disk that dominates our sky, shrinks to a brilliant point among countless others. This isn't just dimmer, it's a completely different relationship with the source of energy that makes planetary systems possible. Shadows, those simple companions of every sunny day on Earth, would barely exist. The contrast between light and dark becomes so subtle that the very concept of shadow loses meaning. Imagine a world where midday looks like deep twilight, where the sky remains dark enough to see stars even when the sun is overhead. It's a reminder that our experience of day and night, of seasons and weather, depends entirely on our specific distance from our specific star. The brightness problem reveals something profound about detection and discovery. A planet can be enormous by our standards and still remain completely invisible simply because of distance. Light follows the inverse square law, meaning that something twice as far away appears 4 times dimmer. By the time you reach distances of several hundred astronomical units, that dimming effect becomes almost incomprehensible. A world that might be easily visible if it orbited where Mars orbits becomes thousands of times fainter than Neptune. This creates a humbling reality for astronomers. Even with our most sensitive instruments, even with exposure times lasting hours, such a distant world might appear as nothing more than a faint dot among millions of other faint dots. The challenge isn't just technical, it's almost philosophical, like trying to find a specific grain of sand on a beach by candlelight. Movement adds another layer to this cosmic hide-and-seek game. Planets closer to the Sun zip along their orbits fast enough that their motion becomes obvious within days or weeks, but orbital speed decreases with distance, following laws that Johannes Kepler worked out centuries ago. A planet hundreds of astronomical units away would crawl along its orbit so slowly that detecting its movement would require observations spanning not days or weeks, but months or years. This glacial pace of motion means that such a world could hide in plain sight, masquerading as a background star in survey after survey. Automated telescopes designed to catch fast-moving asteroids might photograph it dozens of times without recognizing it as a planet at all. The very slowness that helps it remain hidden also speaks to the vast scales of time operating in the outer solar system. Mass estimates for such a hypothetical world range from perhaps 3 Earth masses up to 20 or more, though most calculations cluster around that 5 to 10 Earth mass range. These numbers represent more than just academic curiosity. They hint at gravitational influence operating on scales that dwarf anything in the inner solar system. Gravity, after all, doesn't respect boundaries or require close encounters to make its presence felt. The gravitational influence of a massive distant planet would be persistent and patient, like a conductor leading a very slow orchestra over millions of years, over billions of years. Such a world could gently guide the orbits of smaller objects, creating patterns and alignments that would eventually become visible to astronomers patient enough to map them. This is gravity as a sculptor, working on timescales that make human history seem like a brief moment. The interplay between mass and distance creates a kind of cosmic equation where multiple solutions remain possible. A more massive planet could hide farther away and still produce observable effects, while a lighter world would need to lurk somewhat closer to make its presence felt. This mathematical relationship explains why pinning down exact numbers remains so challenging. Astronomers must work with probabilities and ranges rather than precise measurements. Moons become an intriguing possibility in this distant realm. If such a planet exists, and if it formed through processes similar to those that created Uranus or Neptune, it might host its own small family of satellites. These could be captured objects from the Kuiper Belt, or they could be remnants left over from the planet's own formation billions of years ago. Such moons would be even fainter and more elusive than their parent world, but their existence wouldn't surprise anyone familiar with how planets tend to collect companions. Internal heat sources add warmth to this cold story, literally and figuratively. Even at such enormous distances from the Sun, a massive planet might retain heat left over from its formation, or generate new heat through radioactive decay of elements trapped in its core. Uranus and Neptune both emit more energy than they receive from sunlight. Powered by internal processes that operate independently of solar heating, this internal warmth could drive atmospheric circulation, creating weather patterns that operate on completely different principles from Earth's solar-powered climate. Subsurface oceans might exist beneath thick shells of ice, maintained by geothermal energy rather than solar radiation. Everything would proceed slowly, like a movie played at quarter speed, but the fundamental processes of planetary behavior would continue operating. These possibilities expand our mental map of the solar system in profound ways. Instead of imagining space ending with Neptune and then fading into scattered debris, we're forced to consider a much larger and more varied cosmic neighborhood. Distant regions that we've barely begun to explore might contain substantial worlds with their own complex characteristics and behaviors. The discovery of exoplanets over the past few decades has taught us that nature produces far more variety than we initially expected. Before we found planets orbiting other stars, our solar system seemed like a reasonable template for what planetary systems should look like. Instead, we discovered hot Jupiters skimming the surfaces of their stars, super-Earths with no analogue in our neighborhood, and tightly packed systems where multiple planets orbit closer to their star than Mercury orbits our Sun. This diversity serves as a reminder that our expectations often underestimate nature's creativity. A distant, massive planet in a wide, eccentric orbit might seem unusual by the standards of our inner solar system, but it fits comfortably within the broader context of planetary system architecture that we've discovered around other stars. Scientific caution remains essential throughout these speculations. The existence of such a distant world remains hypothetical, supported by intriguing patterns in the data, but not yet confirmed by direct observation. The estimates of size and mass depend on mathematical models that incorporate assumptions about orbit dynamics and the accuracy of current observations. New data could refine these estimates significantly, or potentially challenge the entire hypothesis. This uncertainty doesn't diminish the scientific value of the investigation. It exemplifies how science works at its best. Hypotheses emerge from careful analysis of available evidence, predictions follow from theoretical models, and then more observations either support or challenge those predictions. The process continues, with each new piece of evidence adding to our understanding or forcing us to reconsider our assumptions. The notion of such a world, moving slowly through the outer darkness, captures the imagination precisely because it challenges our assumptions about what we've already discovered. Rather than thinking of the solar system as a completed map with all major features already catalogued, we're invited to consider it as a landscape, still being explored, with distant horizons that might hold genuine surprises. Earth completes its journey around the Sun in exactly 1 year, a rhythm that governs our seasons, our calendars, and how we experience time itself. Mars needs almost double that duration. Jupiter requires nearly 12 of our years, out at Neptune, floating in the frigid outer reaches. One orbit demands 165 years. But these distances pale compared to what lies beyond. A world hundreds of times farther from the Sun than Earth would need, perhaps 10,000 years, maybe 20,000, to complete a single orbit. Since such a planet last occupied its current position, every human civilization would have risen and fallen, all of recorded history would have unfolded, and still this distant world would not have completed one of its own years. This immense time scale transforms the very nature of planetary motion. In our neighborhood, planets sweep along their paths at speeds we can observe, changing position from night to night. A planet, hundreds of times more distant, moves with glacial patience. Its position against the background stars would shift only barely over many months of observation. This sluggish movement explains why such a world could remain hidden for so long. It would not reveal itself through obvious motion, like the planets we know. Its faint reflected sunlight would make it nearly indistinguishable from distant stars. It would simply drift, unhurried and patient, following an orbital path that unfolds on timescales far exceeding human lifetimes. Most models suggest such a planet would not follow a simple circular path. Instead, it would trace an elongated, eccentric orbit. Sometimes it might approach within a few hundred times Earth's distance from the Sun. Other times it could wander more than 1,000 times farther out. Even at its closest approach, the Sun would appear as little more than an intense star, not the broad, bright disk we see from Earth. At its most distant point, sunlight would fade to a cold glow barely sufficient to illuminate whatever surface might exist below. Temperatures in this environment would plunge to extremes. The surface, assuming one exists beneath any atmosphere, would be colder than almost anywhere else in the solar system. Only the most distant comets and dwarf planets experience such frigid conditions. Gases that remain vapors on other worlds, methane, nitrogen, carbon monoxide, would freeze solid, settling as frost and ice. Yet even in this profound cold motion persists. Gravity operates regardless of temperature. Orbital mechanics continue unchanged in the darkness. The planet would maintain its long path, guided by the sun's gravitational influence, unaffected by the surrounding gloom, except in appearance. There is something quietly remarkable about motion persisting on such scales. A planet could spend thousands of years traveling outward, slowing gradually as it climbs against the sun's gravitational pull. Then thousands more years falling back inward, accelerating as gravity draws it closer. The orbit becomes like a slow breath, expanding and contracting over geological ages. During the distant portion of its journey, the planet moves at its slowest speed, lingering in the far darkness for extended periods. This matters because statistically, if such a world exists, we would most likely find it near the farthest part of its orbit. That is where it spends most of its time, simply because it travels more slowly there. Unfortunately, that is also where it would appear faintest and prove hardest to detect. Such an orbit might create seasons, though unlike anything familiar to us. Seasons depend on a planet's axial tilt and its distance from the Sun. Earth's tilt at about 23.5 degrees creates our yearly seasonal cycle, but on a planet with a year lasting 10,000 years, a single season could persist for millennia. Imagine a winter lasting longer than all recorded history, or a summer unfolding so slowly that no civilization could observe both its beginning and end. Temperature changes, already subtle at such distances, would occur gradually beyond ordinary comprehension. The extreme cold and faint sunlight means seasons might not create dramatic surface effects. Differences between winter and summer might be measured in small temperature shifts rather than sweeping climate changes. The orbital tilt itself also matters. Many models suggest this distant planet's orbit would be inclined relative to the main plane of the solar system. Rather than traveling in the same flat disk as most planets, it would rise above and dip below that plane during its long journey. This inclination could explain why some distant objects have unusual orbital tilts. Over millions of years, the gravitational influence of a tilted distant planet could gradually alter the orientations of smaller bodies, nudging them into orbits that differ from the main planetary plane. It is a slow process, but slow processes dominate the outer solar system. No rapid collisions or dramatic migrations happen now, only the steady pull of gravity shaping orbits over immense spans of time. There is also the question of how such an orbit remains stable. The solar system is not empty. Giant planets, particularly Jupiter and Saturn, exert strong gravitational influences. If a distant planet's orbit brought it too close to these giants, its path could be altered dramatically, perhaps even ejecting it from the solar system entirely. For such a planet to remain bound to the Sun for billions of years, its orbit would need to avoid close encounters. Simulations suggest this is possible if the planet's closest approach remains far beyond Neptune, keeping it safely separated from the strongest gravitational perturbations. This long-term stability is crucial for testing different orbital models. A hypothetical planet that produces the right clustering of distant objects but becomes unstable after a few million years would not convincingly explain what we observe. The real solar system has endured for billions of years, so any proposed configuration must remain stable over comparable timescales. The view from such a world would be extraordinary. The Sun would appear bright but not overwhelming. Giant planets, if visible at all, would look like faint stars. The Milky Way would stretch clearly across the sky, unobscured by atmospheric haze if the planet's atmosphere were thin or absent. Night and day would still exist if the planet rotates, but the difference between them might be subtle, especially at great distances where sunlight is already dim. Stars would dominate the sky, steady and bright, with the sun simply one among many, though still the brightest. Such a world would be profoundly silent. There would be no wind without an atmosphere, no flowing water, no rustling leaves. Any sound requires an atmosphere to carry it. And even then, conditions would be so cold that activity would be minimal. Yet silence does not mean stillness. Beneath the surface, radioactive elements might release heat slowly, warming the interior. Tidal forces from many moons could generate additional heat, though probably weakly. Geological processes might continue at a slow pace, perhaps forming cracks in icy crusts or allowing subsurface layers to remain slightly warmer than the frozen exterior. Even in the coldest parts of the solar system, change continues, only at a pace that stretches far beyond everyday experience. From our perspective on Earth, observing such a planet would require extraordinary patience. Astronomers would need to compare images of the same sky region taken months or years apart, looking for a faint point that shifts slightly relative to background stars. This is meticulous work requiring careful calibration and precise measurements. Modern surveys are improving this process. Large telescopes equipped with wide field cameras can scan vast sky areas repeatedly, building detailed maps over time. Computers analyze these images, searching for tiny movements that might indicate a distant object. Still, the search remains challenging. A planet at the far reaches of its orbit could be so faint it lies near detection limits, indistinguishable from countless distant galaxies that fill deep sky images. This is why the planet hypothesis remains unconfirmed. The planet, if it exists, is not hiding deliberately. It is simply distant, faint, and slow, qualities that make detection difficult but not impossible. There is something calming in the idea of such a world moving steadily through darkness, unaffected by the concerns of the inner solar system, following a path set billions of years ago. It reminds us that the solar system is not a small, compact place, but a vast environment extending far beyond the orbits we usually imagine. As astronomers continue searching, refining models and scanning the sky, the question remains open. A long, cold, silent orbit may be carrying a world we have not yet seen, one that reveals itself only through the gentle gravitational pull it exerts on distant bodies. When we think about undiscovered planets, we often forget just how incredibly vast space really is. The solar system stretches far beyond what most people imagine, and out in those distant regions, darkness dominates everything. Light from our sun becomes weaker and weaker as it travels outward, spreading thin across enormous distances. By the time sunlight reaches Neptune, it's already 900 times dimmer than the light we experience here on Earth. Now imagine going even further out, hundreds of times beyond Earth's distance from the sun. Out there, any planet would catch only the tiniest amount of sunlight, reflecting back just a faint glimmer toward our telescopes. Even a world several times larger than Earth would appear as nothing more than a dim speck, easily lost among the countless stars and distant galaxies that fill our night sky. The challenge of finding such an object becomes even more daunting when we consider how crowded the universe appears through our telescopes. Modern instruments can detect millions of stars in a single patch of sky, each one looking like a tiny dot of light. Searching for one slowly drifting planet among all those stationary points is remarkably similar to trying to spot a single snowflake floating through a blizzard, except these snowflakes are separated by distances so immense that their movement becomes almost impossible to notice. Movement, or rather, the lack of obvious movement, creates another layer of difficulty. Objects closer to the sun dance noticeably across our sky over short periods. We can track asteroids as they shift position over just hours or days, but a planet, lurking in the outer darkness, would creep so slowly across the sky that its position might not change detectably over an entire night of observation. Even over weeks, the movement could remain too subtle for our instruments to register clearly. Astronomers typically identify solar system objects by comparing photographs taken on different nights, looking for those telltale shifts against the background of fixed stars. A distant planet moving at such a glacial pace might require months or even years before its motion becomes obvious. Many sky surveys, especially older ones, simply weren't designed to detect such patient wanderers. They might photograph a region briefly or compare images taken too close together in time to reveal very slow motion. The sheer size of the search area compounds these problems exponentially. The sky surrounds us completely, an enormous sphere of possibilities. And though astronomers have mapped large portions of it, not every region has received equally thorough attention. Some areas prove particularly challenging to study, especially those regions where our view passes through the dense plane of the Milky Way galaxy. There, countless stars and clouds of cosmic dust create a crowded, obscuring background that can easily hide faint objects. If our hypothetical distant planet happens to lie in one of these difficult regions, finding it becomes even more challenging. Its already faint light would be lost among the stellar crowds, requiring careful, repeated observations to distinguish it from the background noise of the universe. This reminds us that discovery often depends not just on having the right tools, but on looking in the right places at the right times. The brightness of any distant world also depends heavily on what it's made of, or what covers its surface. A planet wrapped in bright ice would reflect more sunlight back toward us than one with a dark, light-absorbing surface. If such a planet has low reflectivity, what astronomers call low albedo, it would appear even fainter than we might expect, based on its size and distance alone. There's also the matter of orbital timing. Objects following elongated paths around the Sun spend most of their time at the farthest points of those paths, moving slowly and receiving minimal sunlight. If a distant planet exists and happens to be near that far point right now, it would currently appear at its absolute faintest and most difficult to detect. The cosmic timing might simply be working against us. Temperature adds yet another complication to the search. Very cold objects emit little infrared radiation compared to warmer bodies. Some telescopes hunt for distant objects by detecting their heat rather than reflected sunlight, but a planet at extreme distances might be so cold that even its thermal glow remains frustratingly faint. All these factors combine to create a situation where something large and real could remain hidden, not because it's truly invisible, but because it's dim, slow, and located somewhere in a vast region that hasn't yet received thorough enough investigation. This raises fascinating questions about the nature of discovery itself and what it means for something to exist before we find it. Astronomy, as a systematic science of comprehensive sky surveys, is surprisingly young. Large digital surveys that repeatedly scan the entire sky have become common only within the past few decades. Earlier generations of astronomers worked with photographic plates and much smaller fields of view, making it considerably harder to detect very faint, slowly moving objects. They were pioneers working with the tools available to them, but those tools had significant limitations. Technology continues advancing rapidly, however. New telescopes equipped with wide field cameras can capture enormous areas of sky in single images, and sophisticated software can compare photographs taken at different times, searching for tiny changes in position or brightness. Modern computational power allows astronomers to process vast amounts of data, looking for patterns and movements that would have been impossible to detect just decades ago. The search requires extraordinary patience, though. Data must be carefully processed, thoroughly analyzed, and rigorously verified. Candidate objects need tracking over extended periods to confirm their motion and calculate their orbits. This isn't a process that yields instant results, instead unfolding gradually, often over years of careful observation and analysis. There's something profoundly humbling about realizing that absence of evidence doesn't necessarily constitute evidence of absence. Throughout scientific history, countless objects and phenomena remained undetected until technology improved or new methods emerged. Uranus traveled invisibly overhead for centuries, mistaken for just another star until someone looked more carefully. Neptune was discovered only after mathematical predictions guided observers to exactly the right patch of sky. Even Pluto remained unknown until the 20th century, despite being part of our solar system all along. The outer solar system remains very much a frontier, a region where discoveries continue unfolding regularly. Each year brings identification of new distant objects, refinement of orbital calculations, and improved understanding of how this vast region organizes itself. We're still mapping our own cosmic neighborhood, still finding surprises in what we might assume should be familiar territory by now. Another intriguing possibility involves our own expectations and assumptions. For a long time, astronomers expected any large planet to orbit relatively close to the flat plane where most planets travel. If a distant world follows a significantly tilted orbit, it could spend much of its time far above or below this plane, in regions that weren't primary focuses of earlier surveys. This possibility has influenced modern search strategies, encouraging astronomers to consider wider ranges of potential locations and scan regions that might once have seemed unlikely hiding places. As searches continue, we're reminded that science often progresses through gradual accumulation rather than sudden dramatic revelation. Each new observation contributes to a growing body of evidence, refining models and narrowing ranges of possibilities. A distant planet might someday appear as a faint moving dot in a series of images, its orbit calculated and confirmed through years of patient observation. Alternatively, the hypothesis might eventually be ruled out, replaced by different explanations for observed patterns in distant objects. Either outcome would deepen our understanding of how the solar system works. For now, though, the mystery remains beautifully open, a question that continues guiding observations and inspiring new research into the dark, distant reaches of our cosmic home. Imagine trying to find a single candle flame flickering somewhere in the next county, over on a moonless night, while you're not even sure it's actually lit. That's roughly what astronomers face when they hunt for distant planets lurking at the edges of our solar system. The whole process requires a kind of patience that most of us have never had to develop in our fast-paced world. Modern telescopes work like giant light buckets, gathering photons that have traveled for hours across the solar system. The bigger the mirror, the more light they can collect, and the fainter the objects they can detect. But here's where it gets interesting. These instruments don't just magnify things the way you might expect. They create massive digital photographs, capturing millions of tiny points of light in each exposure. Think about how strange that is for a moment. Each dot of light in these images might represent something incredible. A distant world, an asteroid, maybe even something we've never seen before. But most of the time, these dots just blend into the cosmic background, unremarkable and silent. The real magic happens when computers start comparing these images over time. A distant planet might look completely ordinary in a single photograph, just another faint speck among thousands. But planets move, even if they move incredibly slowly. Over weeks and months, that movement becomes detectable, like watching the hour hand creep around a clock. Face. Motion matters more than brightness in these searches. A dim object that shifts position against the background stars reveals itself as something special, something orbiting our sun from the cold depths of space. This means astronomers have to photograph the same patches of sky over and over again, creating what amounts to a cosmic time-lapse movie. The Vera Rubin Observatory in Chile represents one of the most ambitious attempts at this kind of systematic sky watching. It uses one of the largest digital cameras ever built, capturing enormous sections of the night sky in extraordinary detail. Night after night, it photographs the same regions, building up a historical record of how everything moves and changes. There's something almost meditative about this process. The telescope operates with mechanical precision, pointing, photographing, moving on to the next target. Meanwhile, distant objects creep along their ancient orbits, most of them following paths that were set billions of years ago. The intersection of human technology and cosmic time creates a unique form of patience. Each image contains far more information than any human could process. Automated software scans through the data, measuring positions, tracking changes, flagging anything that looks unusual. but even the computers need time to be certain. A faint object detected once could be an instrument artifact, a cosmic ray hit, or just random noise. Only repeated observations can confirm that something is really there. The Subaru telescope in Hawaii takes a different approach, focusing its searches on specific regions where orbital models suggest a hidden planet might lurk. This targeted strategy acknowledges a fundamental challenge. The sky is unimaginably vast. Even when you narrow down the search area using the best available theories, you're still looking through an enormous volume of space. Some telescopes search in infrared light, detecting heat rather than reflected sunlight. The WISE survey scanned the entire sky this way, finding countless asteroids, comets, and failed stars called brown dwarfs. But a planet hundreds of times farther from the Sun than Earth would be incredibly cold, barely glowing with thermal energy. Even our most sensitive instruments struggle to detect such faint heat signatures. There's also a kind of archaeological aspect to this work. Astronomers regularly return to old images, reanalyzing them with improved techniques and more powerful computers. Sometimes discoveries hide in plain sight, waiting in photographs that were taken years earlier. The object was there all along, but the tools or methods needed to recognize it hadn't been developed yet. This raises an intriguing possibility. Somewhere in the vast archives of astronomical images, a distant planet might already be recorded, just waiting for the right analysis to reveal it. The night sky has been photographed countless times over the decades, creating an inadvertent historical record of slow-moving objects. One of the trickiest challenges involves distinguishing planets from distant galaxies. In a single image, both can appear as tiny, faint smudges of light. Only motion separates them over time. Galaxies stay put, relative to other distant objects, while planets trace slow paths against the stellar background. This is why repeated observations become absolutely crucial. Weather adds another layer of complexity to ground-based searches. Clouds, atmospheric turbulence, and the natural glow of our atmosphere all interfere with observations. Some regions of sky are only visible during certain seasons, and bad weather can interrupt critical follow-up observations. Space telescopes avoid these problems but have their own limitations, including restricted observation time and smaller fields of view. The dense star fields of the Milky Way create their own difficulties. When you're trying to spot a faint object against a background crowded with stars, the extra light creates noise that can mask your target. If a distant planet happens to be located in one of these busy regions of sky, it might remain hidden simply because the observing conditions make detection nearly impossible. Despite all these challenges, the work continues with quiet determination. Each year brings new discoveries of trans-Neptunian objects, small worlds orbiting beyond Neptune. Every new orbit that gets calculated helps refine our models of the outer solar system and potentially narrows the search area for larger, more distant planets. There's something deeply human about this persistence in the face of such enormous odds. Astronomers around the world share data, combine observations from different telescopes, and discuss their findings at conferences and in research papers. The search for distant worlds has become a global collaboration, linking observers across continents and time zones. Consider the strange intimacy of this work. People spend their careers studying objects so distant and faint that they exist at the very edge of detectability. These worlds, if they exist, receive almost no heat from the sun and probably haven't changed much since the solar system formed. They represent time capsules from the earliest days of planetary formation, preserved in the deep freeze of interstellar space. New technology continues to push the boundaries of what's possible. Larger mirrors collect more light, more sensitive detectors can spot fainter objects, and increasingly powerful computers can process ever larger datasets. Surveys that would have been completely impossible just a generation ago now run routinely, scanning millions of stars and tracking thousands of moving objects. But astronomers remain appropriately cautious about their findings. The fact that a predicted planet hasn't been found yet doesn't prove it doesn't exist. The outer solar system is so vast and so poorly explored that major discoveries could still be waiting out there. At the same time, The orbital patterns that originally suggested a hidden planet might have other explanations that we haven't considered yet. This uncertainty is part of what makes the search so fascinating. We're probing the very edges of our cosmic neighborhood, using the most sophisticated tools our species has ever created, looking for worlds that might be there or might not. The process itself reveals something important about how science works, how we build knowledge slowly and carefully, one observation at a time. In the end, whether or not these distant planets exist, the search for them has already taught us enormous amounts about the outer reaches of our solar system. Every faint object discovered, every orbit calculated, every negative result adds to our understanding of how planets form and evolve over cosmic time. The journey of discovery continues, patient and methodical, guided by curiosity about what might be waiting in the darkness beyond. When scientists look out into the far reaches of our solar system, they find themselves wrestling with one of the most fundamental questions in research. How do you know when you've found the right answer? The distant objects beyond Neptune seem to cluster in unusual patterns, and while a hidden ninth planet offers an elegant explanation, science demands that we consider every possibility before settling on any single answer. This cautious approach reveals something profound about how knowledge actually develops. Truth rarely announces itself with fanfare. Instead, it emerges slowly through a process of elimination, where competing ideas battle against evidence until only the strongest survive. The clustering of these distant icy worlds could indeed point to a massive hidden planet, but it might also tell a completely different story. Observational bias presents one of the most subtle challenges in astronomy. When we point telescopes at the night sky, we're not scanning every region equally. Some areas get more attention than others. Some surveys work better in certain brightness ranges, and these differences can create patterns that look meaningful, that actually reflect where we've been looking, rather than what's really out there. Think about trying to understand how people distribute themselves across a city by only surveying one neighborhood. You'd get a skewed picture that tells you more about your method than about reality. The same thing happens when hunting for distant solar system objects. If certain orbits are easier to detect than others, the sample we collect might not represent the true distribution of bodies in space. Research teams have spent considerable time analyzing these detection biases. They've studied telescope pointing patterns, examined how sensitivity changes across different sky regions, and calculated the probability of discovering objects in various orbital configurations. Some studies suggest that observational bias could explain at least part of the clustering we see. Others argue that even accounting for these effects, the pattern remains statistically robust. The debate continues as new surveys come online and detection methods improve. Each additional data point helps clarify whether we're seeing a real phenomenon or an artifact of our observational limitations. This uncertainty might feel frustrating, but it actually represents science working exactly as it should. Another intriguing possibility involves the collective gravitational influence of many smaller bodies rather than one large planet. The outer solar system contains countless objects, from dwarf planets to tiny icy fragments. Over millions of years, their combined gravity could influence orbital patterns in subtle but detectable ways. This self-gravity hypothesis suggests that if enough mass were spread among many distant objects, their collective pull might create the clustering we observe. Current estimates indicate that known objects in these remote regions probably don't have sufficient total mass to produce such effects, but many bodies in the outer solar system remain undiscovered. The inventory is far from complete. The early history of our solar system adds another layer of complexity to this puzzle. Billions of years ago, the Sun formed within a cluster of young stars, all condensing from the same vast cloud of gas and dust. During that chaotic period, stellar neighbors passed much closer than they do today. A near encounter with another star could have gravitationally disturbed the outer solar system, pulling objects into the elongated orbits we see now. Such an ancient stellar flyby might explain the existence of objects like Sedna, whose extreme orbit doesn't fit well with interactions involving only the known planets. If a passing star influenced the distant solar system long ago, it could have created a population of objects with similar orbital characteristics, producing apparent clustering without requiring any hidden planet. The migration of giant planets provides yet another potential explanation. Jupiter, Saturn, Uranus, and Neptune probably didn't form exactly where we find them today. Computer models suggest these massive worlds moved inward or outward over time, gravitationally scattering smaller bodies and reshaping the entire solar system architecture. This period of planetary migration could have flung objects into distant orbits that still retain signatures of those ancient interactions. The clustering we observe might be a fossil pattern, a relic of events that occurred billions of years ago, rather than ongoing influence from a planet that exists today. In this scenario, we're looking at archaeological evidence preserved in orbital mechanics. Our understanding of gravitational dynamics at such extreme distances remains incomplete. Effects that are negligible near the Sun can become significant over millions of years in the outer solar system. The gravitational influence of the Milky Way itself, known as the galactic tide, may play a role in shaping distant orbits. This galactic tide arises because our solar system sits embedded within the galaxy's gravitational field. Over long timescales, this field can perturb orbits of objects in the Oort cloud and may also influence bodies in the scattered disk beyond Neptune. While these effects are generally weak, the time involved is enormous. Given enough time, even gentle forces can produce noticeable changes. Some researchers have explored whether the galactic tide, combined with gravitational influences from stars passing near the solar system over billions of years, could create patterns similar to those attributed to the hypothetical ninth planet. Most models suggest these effects alone are unlikely to produce the specific clustering observed, that the question remains open for investigation. Statistical chance offers another sobering possibility. Human minds excel at recognizing patterns, sometimes even when those patterns lack true significance. When dealing with small samples, coincidences can appear meaningful, simply because there aren't enough data points to reveal the actual distribution. This is why astronomers emphasize discovering more objects. Each new observation helps clarify whether a pattern represents reality or illusion. If clustering persists as the sample grows, it becomes more convincing. If it fades, it may have been a mirage created by limited data. Recent years have brought additional discoveries of extreme trans-Neptunian objects, and many of them seem to support the clustering hypothesis. Though the sample remains relatively small, researchers carefully analyze each new find to see how it fits into the overall picture, knowing that a single discovery could shift the entire interpretation. There's also a more speculative possibility that occasionally surfaces in scientific discussions. Some researchers have wondered whether the clustering might result from a massive disk of small objects, an extended belt of material far beyond Neptune, whose collective gravity influences distant orbits. While theoretically possible, this scenario would require a large amount of mass, far more than observations have detected so far. Finding such a disk would present significant observational challenges, and current data don't strongly support this explanation. Still, the outer solar system holds many secrets, and assumptions about what exists out there continue to evolve. The presence of alternative explanations doesn't weaken the ninth planet hypothesis. Instead, it strengthens the scientific process by ensuring all possibilities receive consideration and testing. The goal isn't proving one idea correct, but finding the explanation that best matches available evidence. There's something deeply reassuring about this methodical approach. It reminds us that science isn't about rushing toward conclusions, but about patiently gathering data, testing ideas, and allowing understanding to emerge gradually. Knowledge builds slowly, brick by brick, with each new observation adding to the foundation. This careful methodology reflects a profound truth about how we come to understand our universe. Reality doesn't reveal itself easily or quickly. It requires persistent questioning, rigorous testing, and the humility to admit when we don't yet know the answer. The clustering of distant orbits presents a genuine mystery, one that may take years or decades to solve definitively. For now, the ninth planet remains one of several possible explanations for what we observe in the outer solar system. It's a compelling possibility, supported by computer simulations and consistent with many observations, but it's not yet confirmed. Alternative explanations continue receiving serious consideration, and new discoveries may shift the balance of evidence in unexpected directions. The outer solar system remains a realm of quiet mysteries, where faint objects drift through darkness and clues accumulate slowly. Year by year, each new observation adds a piece to an enormous puzzle, bringing us incrementally closer to understanding what happens at the far edge of the sun's gravitational influence. In that patient accumulation of knowledge, we find both the challenge and the beauty of scientific discovery. Stars don't form in isolation, sitting alone in the vast emptiness of space. They're born in clusters, crowded neighborhoods, where dozens, sometimes hundreds of young suns emerge from the same enormous cloud of gas and dust. The sun wasn't any different. It had siblings, stellar brothers and sisters that shared its birthplace billions of years ago. In these cosmic nurseries, stars huddle much closer together than they do today. While we measure distances between stars in trillions of kilometers now, back then they might pass within just a few 100 billion kilometers of each other. That's still an unimaginable distance for us, but in astronomical terms, it's practically next door. Each young star in these clusters carries its own disk of material, the raw ingredients for planets, asteroids, and comets. But here's where things get interesting. These disks don't exist in perfect isolation. When stars pass close to one another, their gravitational fields reach out and disturb each other's planetary construction zones. They pull, they push, they reshape entire solar systems in the making. Sometimes, in these gravitational dances, something remarkable happens. A planet that's orbiting one star can get nudged just enough that it breaks free and becomes captured by a different star entirely. Computer simulations show us that this planetary theft is possible, though it's certainly not common. The timing has to be perfect, the speed's just right, the distances precisely calculated by the invisible hand of gravity. This brings us to a fascinating possibility about our mysterious ninth planet. What if it didn't form here at all? What if it's an immigrant? A world that spent its childhood circling a completely different star before somehow finding its way into our solar system. The idea might sound like science fiction, but the physics checks out. A captured planet wouldn't follow the neat, orderly rules that govern the worlds born here. It wouldn't necessarily orbit in the same plane as Earth, Mars, and Jupiter. Its path could be tilted, stretched into an elongated ellipse, carrying the signature of its chaotic arrival. This matches perfectly with what astronomers expect to find when they eventually locate Planet 9. The elegance of this scenario is striking. Instead of being a leftover from our own solar system's formation, Planet 9 could be an interstellar traveler, a world that once knew different skies, different constellations, maybe even different physics in its original stellar environment. Every planet carries chemical fingerprints from its birthplace, traces of the specific mixture of elements that existed in its parent star's disk of material. If Planet 9 formed around another star, its composition might tell that story. The ratios of ice to rock, the blend of gases in its atmosphere, the isotopic signatures locked in its core, all of these could differ subtly from Neptune or Uranus. Of course, reading these chemical signatures would require us to actually observe the planet directly, something that remains far beyond our current abilities. The stability question is crucial, though. When a planet gets captured, it usually starts with a wild, highly stretched orbit that takes it on extreme journeys through space. For Planet 9 to still be with us after billions of years, that chaotic path would have needed to settle down over time. Gravitational interactions with the other planets, the subtle influence of passing stars, even the gentle tug of the entire galaxy, all of these forces sculpt and modify planetary orbits over cosmic timescales. Computer models suggest that under the right conditions, a captured planet could indeed find a stable home. If its closest approach to the Sun stays well beyond Neptune's orbit, and if its farthest point extends hundreds or thousands of times Earth's distance from the Sun, it could remain gravitationally bound for the entire age of the solar system. But the window of opportunity for such captures was narrow. The Sun's birth cluster probably scattered after just a few 100 million years as the young stars drifted apart into the galaxy's spiral arms. Any planetary kidnapping would have had to happen during that brief cosmic moment when stellar encounters were still possible. The rarity of these events gives some astronomers pause. The conditions needed for capture are extremely specific, like threading a needle while riding a roller coaster. It might be more likely that Planet 9 formed here and was simply scattered outward by gravitational interactions with Jupiter or Saturn during the solar system's violent youth. Yet the capture hypothesis offers something profound, a reminder that planetary systems aren't isolated islands floating in space. Stars move, they encounter each other's, they exchange material, and influence each other's evolution in ways we're only beginning to understand. The boundaries between one solar system and another aren't as rigid as we might imagine. This connects to a larger cosmic phenomenon that astronomers have been discovering. The galaxy is populated with rogue planets, worlds that drift through interstellar space without any star to call home. These cosmic wanderers were likely ejected from their birth systems during periods of gravitational chaos. If planets can be thrown out, logic suggests some might also be captured under the right circumstances. The galaxy might contain billions of these silent travelers, dark worlds moving invisibly between the stars, carrying no light of their own. The possibility that one of them found sanctuary in our solar system, that it's been quietly orbiting our sun for billions of years in the cold darkness beyond Neptune, adds a poetic dimension to the mystery. There's something humbling about imagining our solar system as less of a closed family and more of an adoptive home. If Planet 9 exists and if it came from elsewhere, it would be a permanent reminder that we're part of something much larger, a galaxy where worlds can migrate between stars like birds following ancient paths across continents. The search continues, with astronomers keeping multiple possibilities in mind. Planet 9 might be a scattered native, pushed outward during our solar system's chaotic youth. It might be a captured immigrant from another star, or it might not exist at all, with the strange orbital patterns of distant objects having some completely different explanation we haven't thought of yet. This uncertainty isn't a failure of science, it's how discovery works. We propose ideas, test them against observations, refine our models, and slowly narrow down the possibilities. Each hypothesis teaches us something new about how planetary systems form and evolve, regardless of which one ultimately proves correct. The process itself reveals something beautiful about the universe, that it's far more dynamic and interconnected than it first appears. Planets don't just form and stay put, they migrate, they get scattered, they can even change families entirely. The solar system we see today is the result of billions of years of gravitational choreography, a dance so complex that we're still learning its steps. The solar system we thought we knew might be just a fragment of something much larger. Finding a ninth planet wouldn't simply mean adding another dot to our celestial maps. It would unravel the story we've been telling ourselves about our cosmic home for generations. Right now, astronomers describe our solar system like a well-organized library. Rocky planets sit close to the sun, giant planets dominate the middle shelves, and debris belts mark the boundaries. Far beyond that, the Oort cloud stretches into space like a vast invisible sphere of sleeping comets. Everything seems to have its place, neat and orderly. But imagine discovering a massive world hundreds of times farther from the sun than Earth. This planet would exist in a realm we barely understand, bridging the gap between our familiar neighborhood and the deep cosmic wilderness. Suddenly, our solar system wouldn't end where we thought it did. The planetary region would extend far beyond Neptune, far beyond the Kuiper belt, into distances that dwarf our usual sense of scale. This discovery would force us to rethink how planets form in the first place. Current theories must explain why planets exist where they do, and how they got there. A distant giant planet, several times heavier than Earth, following a stretched-out orbit, would challenge those models. Scientists would need to figure out how such a world could form, survive, and remain stable for billions of years. The answer might lie in the chaotic early days of our solar system. Computer simulations suggest the giant planets didn't always occupy their current positions. They migrated, interacted with disks of debris, and possibly scattered other planets into oblivion. If Planet 9 formed closer to the Sun and got ejected outward, it would be living proof that our solar system once resembled a cosmic pinball machine. This wandering planet would be like a fossil, a survivor from an era when worlds collided and gravitational forces reshaped everything. It would tell us that the orderly system we see today emerged from violence and chaos. There's something humbling about that thought, that stability can arise from such turbulent beginnings. The outer solar system would suddenly make more sense too. Astronomers have been puzzled by strange objects beyond Neptune, bodies with unusual orbits that seem to cluster in peculiar ways. Some follow paths tilted at odd angles, others maintain distances that shouldn't be stable. A massive, distant planet could explain these anomalies through its gravitational influence. Instead of a collection of cosmic mysteries, we'd have a unified explanation tying observations together. Long-period comets, those visitors that swing through the inner solar system every few thousand years, might also have their origins clarified. A distant planet could nudge objects in the outer solar system, sending them on journeys toward the Sun. This process would add another layer to our understanding of how material moves through space over vast timescales. The discovery would also change how we compare our solar system to others. Planets larger than Earth, but smaller than Neptune, appear to be incredibly common around other stars. Our system has always seemed unusual for lacking such a world between Earth and Neptune. Planet 9 might fill that gap, just in a completely different location. This would suggest that certain processes of planet formation might be more universal than we realized. Our concept of the solar system's boundaries would shift dramatically. Most people think of it ending at Neptune, or perhaps the Kuiper Belt. But the Sun's gravitational influence actually extends much farther, encompassing the distant Oort cloud and beyond. A confirmed Planet 9 would make those outer regions feel more connected, less like empty void and more like structured territory with multiple layers of objects. The practical implications would be fascinating too. Although such a distant world lies far beyond current spacecraft capabilities, its discovery would inspire new technologies and mission concepts. Advanced telescopes might eventually image its atmosphere or detect its thermal signature. Even from Earth, improved instruments could reveal details about its composition, temperature, and the physics of extremely cold environments. There's a profound time dimension to consider as well. A planet with an orbital period of 10 or 20,000 years operates on a completely different rhythm than anything we're used to. It reminds us that celestial mechanics unfolds on timescales that exceed human civilization. Some cosmic processes are so gradual that their full patterns become visible only through patient observation across generations. The discovery would inevitably raise new questions. If one distant planet exists, could there be others? Might the outer solar system harbor additional massive bodies in even more remote orbits? While current evidence doesn't strongly support such possibilities, finding one unexpected world would encourage astronomers to keep searching, to keep pushing the boundaries of the known. Yet the discovery wouldn't solve every mystery. The outer solar system would remain complex and dynamic, shaped by countless processes, acting over billions of years. Planet 9 would be one piece of an enormous puzzle, important but not complete. Cultural and philosophical dimensions would emerge as well. New planet discoveries have always expanded human imagination. From Uranus in the 18th century to Neptune and Pluto, each new world has stretched our sense of place in the universe. A confirmed Planet 9 would remind us that exploration isn't finished, that mysteries still wait in our own celestial neighborhood. It would demonstrate how science progresses through patient observation and careful reasoning, through the willingness to question what we think we know. This isn't about sudden breakthroughs alone, but about the slow accumulation of evidence and understanding. The way we visualize our solar system would transform completely. Familiar diagrams would need massive revision, showing scales far larger than most illustrations convey. The true distances involved would become apparent, emphasizing just how vast the region around our Sun really is. Perhaps most inspiring is the simple fact that new worlds might still be found not by traveling to distant stars, but by looking more carefully at the space that already surrounds us. Our solar system remains a place of discovery, a reminder that the universe holds secrets even in our own backyard. This possibility connects us to something larger, to the countless planetary systems discovered around other stars, to the processes that shape worlds throughout the galaxy. It suggests that our corner of space participates in universal patterns of formation and evolution, that we're part of something much grander than we previously imagined. For centuries, astronomers had only one example to work with when studying how planets behave: our own solar system. It was like trying to understand every forest on Earth by examining just a single grove of trees. This limitation shaped every theory about planetary formation, migration patterns, and gravitational interactions. Everything changed in the 1990s, when telescopes began detecting planets around distant stars. The first discoveries were puzzling, revealing massive gas giants hugging their stars so closely they complete orbits in mere days. These hot Jupiters, as they're called, challenged everything. Scientists thought they knew, because nothing like them exists in our neighborhood. As more exoplanets emerged from the data, a startling picture took shape. Planetary systems display extraordinary variety, far beyond what anyone had imagined. Some stars host multiple worlds packed together, all orbiting closer than Mercury does to our Sun. Others feature giant planets following stretched, elliptical paths, swinging far out into space, then diving back toward their stars. Many systems contain something our solar system seems to lack entirely: planets called super-Earths or mini-Neptunes. These worlds fall between Earth and Neptune in size, and they appear to be among the most common planetary types in the galaxy. This discovery alone suggests our solar system might be somewhat unusual, perhaps even rare in certain ways. The absence of super-Earths in close solar orbits, the relatively circular paths our giant planets follow, and the generous spacing between worlds, these features aren't universal at all. And the generous spacing between worlds, these features aren't universal at all. And the generous spacing between worlds, these features aren't universal at all. And the generous spacing between worlds, these features aren't universal at all. The contraplan, the contratime, in this broader cosmic context, the idea of Planet 9 becomes less extraordinary, more plausible. Distant, massive planets following elongated orbits appear regularly in other systems. Telescopes have detected worlds orbiting hundreds of astronomical units from their stars, so far away they receive almost no starlight. These observations reveal that planetary systems can extend much farther than once thought, with outer regions populated by large, slowly moving worlds. One key insight from exoplanet research involves planetary migration, the movement of worlds from their birthplaces. Young planets don't always stay where they form. Interactions with the swirling disk of material around young stars, gravitational battles with other planets, or encounters with passing stars can dramatically alter their orbits over time. Some planets spiral inward, becoming those mysterious hot Jupiters. Others get flung outward, settling into distant, cold orbits. If Planet 9 exists, it might represent exactly this kind of migration story, a world that formed closer to the Sun, then got scattered outward during the solar system's chaotic early history. This process appears to be common throughout the galaxy, shaping planetary architectures over millions of years. The gravitational dance of planetary formation rarely leaves things where they started, creating the diverse arrangements we observe today. Another lesson from exoplanet discoveries involves hidden worlds. Detection methods have limitations, and planets often remain invisible because they're too small, too distant, or oriented in ways that make observation difficult. As techniques improve, astronomers frequently discover additional planets in systems once thought to contain only a few worlds. This pattern reminds us that our knowledge of the solar system might also be incomplete. Just as unexpected planets appear around other stars, we might still find surprising worlds closer to home, lurking in regions we haven't examined carefully enough. There's a fascinating parallel involving debris disks around young stars. Many are surrounded by broad belts of dust and icy material, similar to our Kuiper belt. These disks sometimes show gaps, warps, or lopsided structures, suggesting unseen planets are sculpting the material through gravity. In several cases, planets have been inferred from these patterns before being detected directly. The planet's gravity creates signatures that astronomers can observe, even when the world itself remains hidden. The Planet 9 situation mirrors this process. Instead of observing dust patterns, astronomers studied the orbits of icy bodies in the outer solar system. Instead of gaps in a disk, they see clustering and unusual orbital tilts among these distant objects. In both scenarios, gravity leaves fingerprints that can reveal hidden worlds, demonstrating how invisible forces shape visible structures across vast distances. Orbital inclination provides another point of comparison. Many exoplanets follow paths tilted relative to their star's equatorial planes, some even orbiting backward, opposite to the star's rotation. These configurations suggest planetary systems can be dynamically complex, shaped by interactions and disturbances that tilt orbital planes away from their original alignments. If Planet 9 has a significantly tilted orbit, it would fit this broader pattern of dynamical diversity. It would show that our solar system, like others, has experienced events that disrupted the original orderly arrangement of planetary orbits, adding another chapter to the story of cosmic chaos and reorganization. The question of scale also matters. Our solar system's known planets occupy a region extending about 30 astronomical units from the Sun, roughly Neptune's distance. But exoplanet discoveries reveal that planetary systems can stretch much farther into space. Some directly imaged exoplanets orbit hundreds of astronomical units from their stars, in environments where starlight barely registers and orbital periods stretch across thousands of years. These distant worlds remind us that planets can exist in regions once considered too sparse or cold for world formation. If such planets are possible elsewhere, it becomes easier to imagine one existing in our own system. The discovery of Planet 9 would place our solar system more firmly within the range of architectures observed throughout the galaxy, suggesting that distant, massive planets are not unusual, but part of nature's planetary diversity. At the same time, such a discovery would provide a valuable research opportunity. Exoplanets, especially distant ones, are difficult to study in detail. We often know only their mass, orbit, and perhaps a few atmospheric properties. A distant planet in our own system, though still far away, would be much closer than any exoplanet, allowing for detailed observations over time. Studying such a world could teach us about planetary atmospheres at extremely low temperatures, the behavior of ice and gas under faint starlight, and the long-term evolution of planetary orbits in stellar systems' outer regions. It would serve as a natural laboratory for understanding conditions that exist throughout the galaxy. There's a deeper philosophical perspective worth considering. For much of human history, our solar system was viewed as a unique, orderly arrangement, a kind of cosmic standard against which other systems might be measured. The discovery of exoplanets has shattered this assumption, revealing that planetary systems are neither uniform nor predictable. They're shaped by complex histories, chance events, and gravitational interactions that produce an enormous range of outcomes. No two systems are exactly alike, and what we once considered normal might actually be quite special. Planet 9, if it exists, would serve as another reminder of this diversity. It would demonstrate that our own system has its unusual features, its own history of migration, scattering, and perhaps even planetary capture from interstellar space. This broader context helps frame the search for Planet 9 in proper perspective. It's not simply about finding another world to add to the planetary census. It's about understanding how planetary systems form and evolve, how common certain configurations might be, and how our solar system fits into the larger story, unfolding across the galaxy. The search represents humanity's ongoing effort to understand our place in the universe, not just as inhabitants of Earth, but as residents of a planetary system that may be far more dynamic and complex than we ever imagined. Astronomy teaches us that patience isn't just a virtue, it's a requirement. The universe operates on timescales that dwarf human experience, and every major discovery reflects this reality. When we think about distant planets, we're looking at objects that might take thousands of years to complete a single orbit around the Sun. We catch only the tiniest glimpse of their cosmic dance. The outer regions of our solar system stretch beyond imagination. Light itself, traveling at the fastest possible speed, takes hours to reach these remote territories. From Earth, studying these distant worlds feels like trying to examine a grain of sand on a beach. From miles away, using only the faintest reflections of light, this immense scale shapes how astronomical discoveries unfold. A researcher might spot a faint dot of light moving slowly against the stars. That single observation represents just the beginning of what could become years of careful work. The object's position must be measured repeatedly. Month after month, season after season, each new measurement refines our understanding of where this distant world travels through space. Trans-Neptunian objects, those mysterious residents of the solar system's outer reaches, present particular challenges. These worlds are so far from the Sun that they receive almost no sunlight. What little light they do reflect back toward Earth appears incredibly dim, fainter than the most distant stars visible to the naked eye. Detecting them requires some of the most sensitive instruments humans have ever built. The story of Neptune itself illustrates this patient approach to discovery. Long before anyone saw the planet directly, astronomers noticed something odd about Uranus. This ice giant seemed to wobble slightly in its orbit, as if some unseen force was tugging at it. Years of careful observation revealed a pattern in these wobbles. Mathematical calculations suggested where an unknown planet might be hiding. Even then, the actual search took time, requiring methodical examination of star fields until Neptune finally revealed itself. Modern planet hunting follows similar principles but with tools that would seem miraculous to earlier generations. Digital cameras can detect objects millions of times fainter than anything visible to the human eye. Computer programs can compare thousands of images, looking for tiny movements that might indicate a distant world. Yet, even with these advances, the fundamental challenge remains the same. Time, the search for what some call Planet 9, emerged from this same patient process. Over many years, astronomers discovered numerous small, icy objects in the outer solar system. Each discovery added another piece to a growing puzzle. These objects, some taking centuries to orbit the Sun, seem to share certain orbital characteristics. Their paths through space appeared aligned in ways that seemed unlikely to occur by chance. Recognizing patterns in astronomical data requires what we might call trained intuition. Early observations might show only scattered points of light, each following its own path through the darkness. But as more objects are discovered, subtle relationships begin to emerge. Several distant worlds might share similar orbital orientations. Their closest approaches to the Sun might cluster in one region of the sky. These patterns hide in plain sight until enough data accumulates to make them visible. Gravitational forces shape these orbital patterns across vast distances and enormous spans of time. A massive planet, even one we cannot see directly, leaves fingerprints in the motions of smaller objects. These gravitational signatures unfold slowly, like ripples spreading across a cosmic pond. Understanding them requires not just observation, but sophisticated computer simulations that model how gravity works over millions of years. The technology behind modern astronomy represents centuries of accumulated knowledge. Telescopes have evolved from simple tubes with glass lenses to complex instruments that can detect individual particles of light arriving from across the solar system. Digital detectors can record images with precision that would have seemed impossible just decades ago. Yet these tools serve the same fundamental purpose that has driven astronomy since ancient times. They help us see farther into the darkness. Survey telescopes now scan the entire sky repeatedly, looking for anything that moves against the background of distant stars. These surveys generate enormous amounts of data. A single night of observation might produce thousands of images, each containing millions of individual measurements. Processing this information requires careful analysis, often involving multiple researchers working together to verify each potential discovery. The collaborative nature of modern astronomy reflects both its complexity and its global scope. Discoveries made at one observatory are quickly shared with researchers around the world. Independent teams verify each other's findings. Computer models developed in one country are tested using data collected on different continents. This international cooperation accelerates progress while ensuring accuracy. Uncertainty remains a constant companion in this work. Early evidence for any new discovery typically comes with significant margins of error. Position measurements might be precise to within fractions of an arcsecond, but even tiny uncertainties can translate into huge differences in calculated orbits. Alternative explanations for observed patterns must be carefully considered and tested. The scientific method thrives on this uncertainty, treating it not as a weakness, but as an opportunity for deeper understanding. Hypotheses are proposed, tested, refined, and sometimes discarded entirely. Each cycle of this process brings us closer to reliable knowledge. In the case of distant planets, this might mean decades of observation before we can speak with confidence about what exists in the outer solar system. Data archives in astronomy span generations. Photographic plates from the early 20th century still provide valuable information for modern research. Images taken decades ago can be reanalyzed using current techniques, sometimes revealing objects that were too faint to detect with earlier methods. This continuity across time gives astronomical research a unique character. Today's observations contribute to a record that future researchers will continue to build upon. The human element in astronomy goes beyond just the technical work of operating telescopes and analyzing data. It involves imagination, creativity, and a willingness to consider possibilities that might seem far-fetched. The idea that a large planet might orbit far beyond Neptune requires us to expand our mental picture of the solar system. It challenges us to think about gravitational influences operating across distances that strain comprehension. Scale affects every aspect of studying the outer solar system. The region where Planet 9 might exist covers an enormous volume of space. Searching this region thoroughly would be like looking for a specific grain of sand scattered somewhere across an entire continent. Current surveys have examined only small portions of the sky where such a planet might be found. Even finding Planet 9 would represent just the beginning of understanding it. Determining its mass, composition, and history would require years of additional study. We might need to wait for new generations of telescopes, perhaps even space-based missions, to learn about its atmosphere, magnetic field, or any moons it might possess. The philosophical implications of this slow pace extend beyond astronomy itself. In a world increasingly focused on immediate results and instant communication, the universe reminds us that some questions cannot be rushed. The most profound discoveries often emerge from sustained effort over long periods. This patience isn't passive waiting, but active engagement with problems too complex for quick solutions. Consider how this connects to our broader relationship with time and knowledge. We live in brief moments, but we participate in ongoing conversations that stretch across centuries. The questions we ask today build on work done by previous generations. The observations we make now will inform research conducted long after we're gone. This continuity gives individual contributions meaning within a much larger framework. The search continues, methodical and persistent. New objects are discovered. Orbits are calculated and refined. Computer models are updated to incorporate fresh data. Whether Planet 9 exists or not, this process enriches our understanding of how gravity works across vast distances, how planetary systems form and evolve, and how patient observation can reveal hidden aspects of the cosmos. Each night, somewhere in the world, telescopes point toward the outer solar system, collecting photons that began their journey hours earlier from distant, icy worlds. Those particles of light carry information about places no human has ever seen, about gravitational dances that unfold over geological timescales. In laboratories and observatories, researchers analyze this information, adding it to humanity's growing map of the cosmic neighborhood we inhabit. The story reminds us that exploration takes many forms. Not all discoveries require traveling to distant places. Sometimes the greatest adventures happen when we learn to see familiar territory with new eyes, or when we develop the patience to watch slow changes unfold over time. The outer solar system has surrounded us throughout human history, but only recently have we developed tools sensitive enough to study its distant residents. This gradual process of discovery mirrors other aspects of human understanding. Complex truths rarely reveal themselves all at once. They emerge, piece by piece, through careful observation, thoughtful analysis, and the willingness to revise our ideas when new evidence appears. The search for distant planets teaches us not just about astronomy, but about how knowledge itself grows and deepens over time. The act of looking for something that might not exist creates a unique kind of tension in the mind. It's different from hunting for your keys, where you know they're somewhere in the house. It's also different from watching Jupiter move across the sky, because we already know exactly where Jupiter will be next month. This other kind of searching, this pursuit of the uncertain, occupies a strange middle ground between knowledge and mystery. Throughout human history, people have gazed upward, without understanding what those points of light really were. They didn't know about the immense distances, the nuclear fusion happening inside stars, or whether other worlds might circle them. Questions always came first, then careful guessing, then looking more closely, and only after long stretches of time did real understanding begin to emerge. When we think about Planet 9 today, we're participating in that same ancient tradition. Astronomers aren't following a map with a clear destination marked. Instead, they're tracking clues, following breadcrumbs left by the strange behavior of distant objects. They notice that certain icy worlds, far beyond Neptune, seem to cluster in unusual ways, almost as if something massive is pulling on them from even farther out. Science often gets presented as a collection of finished facts, neat and tidy, ready to be memorized from textbooks, but the actual practice feels much more fluid than that. Researchers spend most of their time working with incomplete information, trying to measure uncertainty rather than eliminate it completely. Sometimes they have to accept that certain questions might remain unanswered for decades. This approach requires a particular kind of patience, mixed with intellectual humility. The universe doesn't owe us explanations on our preferred timeline. It reveals its secrets slowly, often in unexpected ways. There's something oddly comforting about accepting that our current understanding might be incomplete, that tomorrow's observations could change everything we thought we knew. The search for distant planets also stretches our relationship with time in interesting ways. A single survey might take 10 years to complete properly. Some orbits require centuries of careful measurement before we understand them fully. The implications of today's discoveries might not become clear until long after the original researchers have retired. This creates a sense of continuity that spans generations, where each group of astronomers builds on work started by their predecessors. Data collected decades ago often remains valuable today because the sky changes so gradually. Numbers recorded in the 1980s still help modern computers calculate orbital mechanics. Future telescopes will use observations made right now to answer questions we haven't even thought to ask yet. This creates an invisible conversation across time, where astronomers separated by decades collaborate without ever meeting. Human curiosity seems to be a remarkably persistent force. It drives people to cross oceans, climb mountains, and peer deeper into space, often without any immediate practical benefit. The desire to know what lies beyond the current boundary of knowledge appears to be fundamental to how our minds work. Searching for a planet billions of miles away might seem abstract, but it emerges from the same impulse that led ancient explorers to wonder what lay beyond the horizon. Unlike many forms of exploration, astronomy demands accepting that answers arrive slowly. The universe doesn't respond to impatience. Observations can only happen when atmospheric conditions cooperate. Data analysis requires careful, methodical work that can't be rushed. This enforced slowness has its own gentle rhythm, encouraging reflection and long-term thinking. One fascinating aspect of searching without certainty is how often it leads to completely unexpected discoveries. While looking for one specific thing, researchers frequently stumble across something entirely different. The hunt for Planet 9 has already revealed dozens of previously unknown objects in the outer solar system. Each new discovery adds another piece to our map of distant space, showing us structures and patterns that were invisible just a few years ago. Even if Planet 9 turns out not to exist, the search will have been worthwhile. The process itself has expanded human knowledge, revealed new worlds, and taught us more about how our solar system is organized. This highlights something important about scientific inquiry. The value of a good question isn't measured only by the specific answer it produces. Sometimes the journey matters as much as the destination. There's also something reassuring about the fact that mysteries still exist relatively close to home. In an era when satellites have mapped every square meter of Earth's surface, it's remarkable that we might still be missing an entire planet in our own cosmic neighborhood. This suggests that the age of discovery isn't over, that there are still frontiers waiting patiently in the darkness beyond Neptune. This kind of patient searching extends beyond astronomy into many aspects of human experience. Learning something new, creating art, trying to understand complex relationships. These all involve moving forward without complete certainty about the outcome. We rely on hints, intuition, and the quiet belief that understanding is worth pursuing, even when we can't see exactly where the path leads. The natural rhythms of astronomy offer a counterpoint to the hurried pace of modern life. Stars rise and set on their ancient schedule. Planets drift along their orbital paths across months and years. Distant worlds circle their suns in silence, indifferent to human questions yet somehow inviting them. When astronomers point their instruments toward the outer reaches of the solar system, they're participating in a process that connects them to centuries of previous observers. This creates a kind of perspective that encourages patience with uncertainty. Understanding can unfold gradually, across generations, without needing to be forced or rushed. In a world that often demands immediate answers, the slow work of astronomy suggests that some questions are worth living with for a while, worth pursuing even when the outcome remains unclear. The question of Planet 9 ultimately becomes a question about how we approach the unknown in general. How do we balance curiosity with healthy skepticism? How do we keep exploring when definitive answers remain just out of reach? How do we find meaning in the search itself, separate from whatever we might eventually discover? The search for unknown worlds in our solar system unfolds like a slow conversation between scientists and the cosmos. Two paths stretch ahead of us, each holding its own promise. In one direction, evidence might accumulate until a faint speck of light reveals itself as a genuine planet, its orbital dance finally mapped and understood. In the other direction, clues might point somewhere else entirely, teaching us something unexpected about the outer reaches of our cosmic neighborhood. Both possibilities carry equal weight in the scientific process. Knowledge doesn't always arrive in the form we expect. Sometimes the most valuable discoveries come not from finding what we're looking for, but from understanding why we didn't find it. The very act of searching transforms our perspective, even when the search leads us down unexpected paths. Deep in the outer solar system, gravity plays games on scales that challenge our imagination. Tiny worlds, barely visible in our most powerful telescopes, trace paths through space that take lifetimes to complete. Their movements tell stories, subtle gravitational whispers that hint at forces we haven't fully mapped. Yet, these distant objects don't hurry. They follow laws written in the fabric of space itself, patient and precise. Science thrives on this kind of uncertainty. It's not a weakness in our understanding. It's the engine that drives discovery forward. Every unanswered question becomes a doorway to deeper knowledge. Every mystery solved reveals new mysteries waiting beyond. This endless unfolding keeps astronomy alive, keeps it growing, keeps it surprising us with revelations about our place in the universe. The night sky above us appears still and constant, that appearances deceive us in the most wonderful way. Every point of light moves through space on journeys, vast beyond our daily experience. Planets swing around the sun in their eternal dance. Asteroids tumble through the void. Stars drift across the galaxy over timescales that make human history seem like a brief moment. Out beyond Neptune, in the cold darkness at the edge of our solar system, small icy worlds follow paths so large and slow that ancient civilizations could rise and fall in the time it takes them to complete a single orbit. And perhaps, just perhaps, something larger moves out there too, invisible to us, but making its presence known through the gentle tug it gives to smaller worlds. The scale of our solar system challenges every instinct we have about distance and size. Earth sits about 93 million miles from the Sun, a distance that already stretches beyond comfortable comprehension. But Neptune, the outermost major planet, orbits 30 times farther out. The space beyond Neptune extends even farther, a realm so vast and empty that entire worlds could hide there for decades without being noticed. When you consider those distances, the idea of undiscovered planets stops seeming far-fetched. It becomes almost inevitable. Our telescopes have limits, our instruments have boundaries, and space has plenty of room for surprises. The darkness between worlds offers countless hiding places for objects we haven't learned to see yet. Modern astronomy operates on timescales that would test anyone's patience. Discoveries unfold over years or decades, not minutes or hours. Data accumulates slowly, patterns emerge gradually, and understanding deepens one small step at a time. This methodical pace isn't a flaw in the scientific process. It's one of its greatest strengths. Rushing leads to mistakes. Jumping to conclusions creates false answers that have to be untangled later. The astronomers searching for distant planets embrace this deliberate rhythm. They know that the universe reveals its secrets on its own schedule, not ours. Each night of observation adds another piece to an enormous puzzle, and each piece matters, even when it doesn't immediately show us what we want to see. Telescope technology advances with each passing year, giving us eyes that can see deeper into space and detect fainter objects than ever before. Digital sensors capture light with incredible precision, computer programs analyze vast databases of observations, and patterns invisible to earlier generations of astronomers slowly come into focus. These tools don't guarantee discoveries, but they expand the realm of possibility. The search for unknown worlds connects us to a tradition as old as human curiosity itself. Ancient observers tracked planets with nothing but their eyes and simple instruments, yet they mapped the motions of worlds with remarkable accuracy. They understood that patience and careful observation could reveal truths about the cosmos that no amount of speculation could provide. Today's astronomers continue that tradition with more sophisticated tools, but the same fundamental approach. Watch carefully, record precisely, think deeply about what the data might mean.
Sometimes this process confirms what we expect to find.
Sometimes it surprises us with something completely different. Both outcomes advance our understanding in valuable ways. The question of distant planets reminds us that exploration never really ends. Even in our own solar system, in our own cosmic backyard, mysteries remain. Worlds might exist that no human eye has ever seen, following paths that no human mind has ever calculated. The possibility humbles us and excites us at the same time. There's something profound about living in an era when such discoveries remain possible. We're not too late to witness the finding of new worlds, not too far removed from the age of exploration. The map of our solar system isn't finished yet, and we get to watch as new regions are added to it, piece by careful piece. The darkness beyond Neptune holds secrets that may take generations to fully understand. In that vast emptiness, objects drift in slow motion through paths that dwarf anything in human experience. Some of those objects we've found, some we've glimpsed briefly, and some remain completely unknown to us. The cold and distance out there create a natural laboratory for studying gravity, orbital mechanics, and planetary formation. under conditions that exist nowhere else in our solar system. Each new detection in the outer solar system adds another data point to our growing understanding of how worlds form and evolve. These distant objects preserve conditions from the early days of our solar system, frozen in time by the incredible cold of interplanetary space. They carry information about processes that happened billions of years ago, stories written in ice and rock and locked away in the darkness. The search continues, night after night, with telescopes scanning regions of sky where theory suggests unknown worlds might hide. Most of the time, these searches find nothing more than background stars and distant galaxies, but occasionally, very occasionally, they detect something new, something that wasn't there in previous observations, something that might be exactly what astronomers have been hoping to find. The outer reaches of our solar system exist in a kind of cosmic silence that's hard to imagine. Out there, beyond the familiar planets we learned about in school, lies a realm where darkness stretches endlessly. The sunlight that warms our faces here on Earth becomes nothing more than a distant point of light, barely stronger than any other star in the sky. In this frozen wilderness, time moves differently. A single orbit around the sun doesn't take months or even years, it takes millennia. Imagine something so far away that it witnesses the rise and fall of entire human civilizations during just one trip around our star. The patience required by the universe to orchestrate such movements speaks to something profound about existence itself. The way grand processes unfold beyond our everyday perception of time. Scientists have been piecing together clues about what might be hiding in this distant darkness. Mathematical calculations suggest gravitational influences that tug at known objects in ways that don't quite add up. It's like watching leaves rustle in a forest and knowing there must be wind, even when you can't feel it yourself. The numbers tell a story of something massive and invisible, something that pulls and pushes the smaller bodies we can detect. This hypothetical world, if it exists, would experience conditions so alien to our experience that they challenge our basic understanding of what a planet can be. The cold there isn't just winter cold, it's the kind of cold that approaches the fundamental limits of temperature itself. No liquid water could exist, no atmosphere as we know it, no weather patterns driven by solar energy. Just rock and ice, locked in a kind of eternal stillness. Yet, even in this apparent emptiness, motion continues. The dance of gravity never stops, even when performed by objects separated by billions of miles. Every piece of matter in the solar system influences every other piece, creating an invisible web of connections that spans unimaginable distances. It's a reminder that nothing in the universe truly exists in isolation, that even the most remote and lonely objects participate in the greater choreography of celestial mechanics. The search for this distant world requires a special kind of patience that mirrors the patience of the cosmos itself. Telescopes scan tiny patches of sky, looking for the almost imperceptible movement of a point of light against the backdrop of stars. It's detective work on a scale that makes human lifespans seem like brief moments. Researchers dedicate entire careers to tracking objects that might shift position by barely measurable amounts over months of observation. What strikes many people as remarkable is how something so far away can still be considered part of our neighborhood. The boundary between what belongs to our solar system and what belongs to interstellar space becomes blurry when you consider these extreme distances. We're talking about regions where the sun's influence fades to nearly nothing, where the space between particles of matter stretches beyond comprehension. The very fact that we can predict the existence of unseen worlds through mathematics alone reveals something beautiful about the orderliness of natural laws. The same equations that describe a ball falling from your hand also govern the movements of objects trillions of miles away. There's a kind of cosmic democracy in physics, where the fundamental rules apply equally whether you're dealing with something as small as an atom or as vast as a planetary system. This potential ninth planet, should it exist, would represent a kind of cosmic hermit. It would have spent the entire history of human civilization in essentially the same spot relative to the stars, barely moving, barely changing, while empires rose and fell on Earth, while countless generations lived and died. This distant world would have drifted along its path in almost perfect solitude. The implications extend beyond simple curiosity about our cosmic neighborhood. Understanding the outer solar system helps us grasp how planetary systems form and evolve. Each discovery about these remote regions adds pieces to the puzzle of how our entire cosmic environment came to be the way it is. It's like finding old family photographs that help explain the present by revealing the past. Perhaps most humbling is the realization that despite all our technological advances, despite all our scientific knowledge, we're still capable of being surprised by our own backyard. The universe maintains an endless capacity for mystery, even in places we thought we understood completely. This speaks to the fundamental relationship between knowledge and wonder. How each answer we find seems to reveal new questions we hadn't thought to ask. The search continues through long nights of observation, through careful analysis of data, through the slow accumulation of evidence that might one day reveal whether the distant world is real or merely a mathematical ghost. Either way, the process itself teaches us about the nature of discovery, about how understanding emerges gradually from the darkness of ignorance, much like a distant planet might eventually emerge from the darkness of space.
you.